Good evening. Good evening to one and all. So we'll start soon. Some more people are joining with us. Okay. So this is my contact number 96184-61918. 96184-61918. Somebody is asking me. Yeah, I'm uploading the notes in Telegram. I'm uploading notes in Telegram. Okay. Just you put a request to me in Telegram. I will be sending notes to you. Put a request in Telegram. I will be sending notes to you. Yeah. So they will upload in the platform as well as I will be sending you notes in the Telegram also. Just put a request in Telegram to my mobile number. Okay. So we'll wait for 2 more minutes. Yeah. So let's continue with the yesterday class. Yeah, Aryan Vyas, I said you just put a request to me to my number in this, right, to this number in the Telegram. Put a request to me to this number in the Telegram. I will be sending the notes to you. As well as anyhow, our institute will upload the notes in the student portal. Okay, so I think I can start. Yeah, Radha Priya, they will upload in ODS platform also notes. Okay. Yeah, so let's start with the thing. Yeah, let's continue. See, in the yesterday class, we have seen how we can remove the coupled circuit, right? And by following these conditions, we are capable to remove the coupled circuit so that the transformer is going to be represented as a simple series impedance. Okay? Yeah, 1 minute, please. 1 minute. Okay. So let's continue. So we will start with a problem today. We'll start with a problem today. And just to recall the condition what we have mentioned yesterday, Z01 per unit equals to Z02 per unit. Okay? Yeah. So let's take up this problem first. Yeah. So you please go through this one. Go through this question. Yeah. See that? Single phase transformer has primary winding impedance on its primary winding ratings. Primary ratings as 0.1 plus J0.2 per unit. And the secondary winding impedance on its secondary winding ratings is 0.05 plus J0.18 per unit. The effective impedance of transformer referred to the primary side VB dash per unit. It's a very simple question. Very simple question. Okay. See, he said primary winding impedance in per unit form. Secondary winding impedance in per unit form. Actually, these are not the values of Z01 and Z02. What is the name of Z01? Effective impedance referred to primary side, Z01. What is Z02? Effective impedance referred to secondary side. But in this problem, he has given Z1 per unit, how much? Z2 per unit, how much? Okay, yeah, let's write. Let's write in the solution Z1 per unit number. So that is 0.1 plus J0.2, 0.1 plus J0.2 per unit. Next, Z2 per unit is 0.05 plus you have J0.18 per unit. Actually, the Z1 per unit calculated on the base of primary ratings. On primary ratings as base values. Primary ratings as base values. and Z2 per unit was calculated on secondary ratings as base values. Secondary ratings as base values. Okay, all of you getting my words? See, for example, as we said recently, yesterday, primary ratings we are selecting as based on primary side. Secondary ratings we are selecting based on the secondary side. Are you capable to remove the coupled circuit? I need your answer now. I need your answer. Are you capable to remove the coupled circuit? Yes or no? Yes. That's what we said just before starting this class. This one you see. We have selected the ratings itself as base values on the primary. What are the base values on secondary? Ratings of the secondary winding itself. Means if you consider the ratings itself as base values, definitely coupled circuit can be removed. That implies coupled circuit can be removed. Coupled circuit can be removed. Okay, done. Fine. So now I will draw that equivalent circuit individually. Primary winding impedance, secondary winding impedance, like that we will draw. So let's take the primary winding impedance. This is Z1. Okay. So I will show ideal winding on the primary. It's a primary ideal winding, and I'm showing it's a secondary ideal winding. Okay. Now I will show secondary winding leakage impedance is Z2. Okay. So, and this is a common terminal of 0. Common terminal of 0. Next one. This voltage is V1 I am considering. This voltage I am considering as V2, induced EMFs. Okay. We are converting these Z1, Z2, V1, V2 into per unit domain. Z1 I convert into per unit form. Z1 I convert into per unit form. V1 convert into per unit form. V2 also convert into per unit form. Z2 also convert into per unit form. But you know already, by selecting the base values in a proper way, V1, V2 in per unit will be equal. If V1, V2 are equal in per unit form, we can short these two terminals together so that I can show this simply as Z1 per unit connected in series with the Z2 per unit. Z1 per unit connected in series with Z2 per unit. Then what will be the transformer impedance in per unit form? What will be the transformer impedance in per unit form? Z1 plus Z2 in per unit. That is nothing but effective impedance referred to either primary side or effective impedance referred to secondary side. Kindly listen my words. Kindly listen my words. Sometimes in the exam, just they will say transformer impedance is some value in per unit. Transformer impedance is some value in per unit. The meaning of that is the effective impedance in per unit form, either referred to primary side or referred to secondary side. This is what you have to remember. So I'll write in the next slide. Next slide. Therefore, yeah, please copy this one. I'll wait for 5 to 10 seconds. Please copy this quickly. Okay, yeah. So therefore, transformer impedance in per unit form. Impedance in per unit form. You can call this is ZT in per unit. Else you can call effective impedance referred to the primary side in per unit form, or effective impedance referred to the secondary side in per unit form is nothing but primary winding impedance in per unit plus secondary winding impedance in per unit on their respective basis. So simply you have to add these two numbers, 0.15 plus J0.38. 0.15 plus J0.38 per unit. And just you go through the options what we have given. For the options given, effective impedance referred to primary side is asking Z01. That is nothing but summation of Z1 and Z2. So your answer will be C. Okay. So correct option will be C. Correct option will be C, we can say. But Z1 per unit equals to Z2 per unit. Diksha, please kindly go through the statement what I made. Z01 per unit equals to Z02 per unit. That does not mean that Z1 per unit equals to Z2 per unit. I should not say Z1 per unit equals to Z2 per unit. What I should say, effective impedance referred to primary, effective impedance referred to secondary side in per unit form will be equal, not the primary winding impedance and secondary winding impedance. primary and secondary winding impedances in the per unit form may not be equal. May not be equal. In fact, we don't have a relationship between Z1 and Z2 numbers. We don't have a relation between Z1 and Z2 numbers. Yeah, getting Dikshita? Yeah, okay. Next. I want to make one more simple comment on the transformer before proceeding with the next problem. Just look here. Just look here. See, in the absolute form, we have written Z02 in terms of ohms equals to K square into Z01 in terms of ohms here. Z02 in terms of ohms will be equals to K square into Z01 in terms of ohms. I think all of you know this one. But after taking these base values and all in a proper way, after converting these numbers into per unit form, what we have written? Z02 in the per unit domain equals to Z01 in the per unit domain. I think all of you getting. Z02 per unit domain is equals to Z01 in per unit domain. Now the question is, yeah, what is that observation we can make from these two? Anybody? Any observation you can make? First one, Z02 equals to K square Z01. Second one, Z02 equals to Z01. Means what is the value of K square in the second case? What's the value of K square in the second case? 1. Means we can say K equals to 1. So in the per unit form, I can say K square is equals to 1. Means the value of K is equals to 1. Means transformation ratio in the per unit domain is equals to 1. Transformation ratio, per unit transformation ratio is equals to 1. See, which type of transformers will have this transformation ratio as 1? Which type of transformers will have this transformation ratio as 1? What type of transformers? Isolation transformers. Okay. In case of isolation transformers, you can say this transformation ratio equals to 1. See, simply what we are going to conclude here is, with the help of per unit quantities, we are capable to convert a step up or step down, anything, either step up transformer or step down transformer into an isolation transformer. Following all of you. So all the step up and step down transformers we are capable to convert into isolation transformers. If it's an isolation transformer, it will act as a simple series impedance in the electrical equivalent circuit. That's simplification we are doing by using per unit quantities. Okay. Yeah. So let me write in the next slide. With the help of per unit quantities, per unit quantities, the step up and step down transformers, step up and step down transformers in the system can be converted into isolation transformers by choosing proper base values, in bracket, by choosing proper base values. Okay. Yeah. So you please write this statement. We'll take one more problem in the transformer. Is it valid all transformers? What's the meaning of that? Vinita, what's your doubt? Why you consider K per unit? We are writing in per unit domain, right? We are writing that in per unit domain. Aishwarya Venkatesh, delta delta, star star. We are talking about isolation transformer, in the sense we are talking about transformation ratio only, not connection of transformer. Why you considered K per unit means we are writing this in per unit domain. That's why I have written K per unit. If you want, you write K square per unit equals to 1. That's it. That's your wish. Okay, yeah. So let's take one more problem. It's a previous GATE problem as well as asked in IES object examination also one time. Same question almost, maybe with some change in the data, you can say. Change in the data, right? Go through this question. The resistance and reactances of a 100 kVA, comma 11,000 volts by 400 volts. Primary 11,000 volts, secondary 400 volts. Delta star, in the sense primary is connected in delta, secondary is connected in star. Distribution transformer are 0.02 per unit and 0.07 per unit respectively. Means resistance value 0.02, reactance value 0.07. Okay. The phase impedance of transformer in ohms referred to its primary is dash ohms in bracket magnitude. Phase impedance is asking. Phase impedance. Phase impedance of transformer referred to the primary side. Okay. So what's the primary side here? Delta. Means 11,000 volt side you have to consider now. First of all, in the solution, what we will write is the solution. Transformer we have like this. Delta star, primary 11,000 volts, secondary 400 volts. Okay. Resistance of transformer in per unit domain, that is 0.02 per unit. Reactance of transformer in per unit domain, that is 0.07 per unit. Means impedance of transformer in the per unit domain. Impedance of transformer in per unit domain R plus Jx. So 0.02 plus J 0.07 in per unit. 0.02 plus J 0.07 in per unit form. That's the value of ZT in per unit. Yeah, it's 100 kVA transformer. 100 kVA rate. See, actually, listen. As I said just now in the previous problem also, if you see the nameplate details of transformer, just if any transformer is available just beside your home, go safely to the transformer location and just look at the nameplate of transformer. There you can find delta star connections, angles and all, and you can find the resistance in per unit, reactance in per unit. Okay, like this. See, this ZT per unit what you have itself is effective impedance of transformer, either referred to primary side or referred to secondary side, we should say. Means the same number ZT per unit I can call as effective impedance referred to the primary side, which is nothing but 0.02 plus J 0.07 per unit. Okay, very simple. What is asking now? What is that value in ohms? What is that value in ohms referred to primary side? Means simply you take the primary side base value Z base, primary side impedance base, multiply this per unit number with the Z base. You will get the ohmic value. Fine. But one thing, if they have given per unit impedances or per unit resistance and reactance like this, definitely what you have to say is this per unit value is calculated by considering the base values as ratings itself. Getting my words? This per unit value is on which base? This on which base? On ratings as base values. Ratings as base values. By considering ratings itself as base values, we have this ZT value. Means primary side base values are what? 11,000 volts line to line, 100 kVA 3-phase. Okay? Yeah. So base values on primary side means primary winding ratings. Base values on primary side. So you can call V1 base line to line value. It is 11,000 volts. Okay. What is the S1 base? 3-phase value? 100 kVA. That will be remain same on both the primary and secondary sides. Okay, so we have to multiply this Z01 per unit with the Z base per phase. What is the Z base per phase formula? Z base per phase formula, always I will ask you to take this one as D base per phase whole square by S base per phase. D base per phase whole square by S base per phase. It's the Z1 base per phase. What is the V1 base per phase? What's the value of V1 base per phase here? V1 base per phase, it's 11,000 by root 3 volts. What's the S1 base per phase? S1 base per phase will be 100 by 3 kilo. 100 by 3 kV. Okay, you can substitute these two numbers in the Z1 base per phase. I'm really sorry. What is V1 base per phase? That will be equals to 11,000 only. Why it is so means that primary is in delta connection. Primary is in what connection? Delta connection. Okay. Good, good. So primary in bracket to write it is delta. Now you substitute the numbers here quickly. 11,000 whole square in the numerator. Denominator you get 100 by 3 into 10 power 3. Kilo na 10 power 3. You calculate this value. How much? Please calculate this number. So it will be 3630 ohms. 3630 ohms. Okay, now you multiply this number with Z01 per unit so that we can get the phase impedance. Phase impedance, primary phase impedance. So effective impedance or better, we follow the word what they have given in the problem. Phase impedance of transformer referred to primary side. Phase impedance of transformer referred to primary side in ohms, right? So I can call Z01 ohm will be equal to Z01 per unit number multiplied with Z1 base per phase. Z1 base per phase. What's the Z01 per unit? 0.02 plus J 0.07. Z1 base is 3630. Okay, but what is asking in the problem? What is asking in the problem? He is asking to give the option as only magnitude. In the blank, we should fill the magnitude value only. We have to fill the blank only with the magnitude. So you need to calculate magnitude of this number. So I can say magnitude of Z01 ohms per phase, nothing but, of course, magnitude of first complex number, square root 0.02 square plus 0.07 square. Okay, so the magnitude of the second number is 3630 will be in ohms. Okay, you please calculate this number. Anyhow, in the examination, if you are writing GATE exam particularly, you have to do this calculation with virtual calculator. Virtual calculator, but as we are learning now, you use your regular BTech college calculator and calculate this number. Later on, while you are doing the revisions and all, you try to practice these calculations in the virtual calculator. Okay? Yeah. So it's square root 0.02 square plus 0.07 square into 3630. This number is 264.267. 264.267 ohms. Getting all of you? 264.267 ohms. That's the value of Z01 ohms. Okay, you do one thing. As a homework, you try to find out the phase impedance in ohms referred to secondary side also. As a homework. I'm writing here itself. Homework. Calculate phase impedance of transformer in ohms referred to secondary side. Referred to the secondary side, you try to calculate the phase impedance value. Means what you have to do? So Z02 ohms equals to Z02 per unit into Z2 base per phase. Z02 ohm equals to Z02 per unit into Z2 base per phase. Z02 per unit, Z01 per unit, both are equal. You can write as it is into what's the Z2 base per phase? You have to calculate that number in a proper way. You select the secondary side base voltage per phase, secondary side base apparent power per phase, and you calculate Z2 base per phase, multiply that with a per unit number. Yeah, all of you getting this? Sir, if only impedance asked on primary, then we have to take Z3. What is it? Z3 phase? What is the Z3 phase? I don't know. Yeah, I'm showing previous slide. Somebody has asked me to show previous slide. Please kindly complete it. Showing the previous slide. So I think I can move. Okay, you calculate this one. Calculate this one. Yeah, so I'm showing the question. Yeah, I think already I uploaded this file to you in the Telegram. I already uploaded this questions file in Telegram, as well as I will ask the people to upload this file in the what we call student portal also. Yeah. Okay. So so till now we discussed about the transformer conversion and all. Now we are going to think about what are the advantages of using the per unit quantities in the analysis. Okay. Yeah. So let's take in the next slide. Advantages of using per unit quantities. Using per unit quantities in the analysis. Advantages of using per unit quantities in the analysis. What is the first advantage? Just now we are discussing coupled circuits. Coupled circuits of transformer can be removed. Transformer can be removed. So network analysis will become continuous. Network analysis becomes continuous. Number of equations to be solved will be less. Number of equations, maybe KVL equations you can write. Equations to be solved will reduce. Right. So this is one purpose, or you can say advantage right now because of this per unit quantities. Okay. Second advantage I'm going to tell. Second one. See, actually, is this Bhavani, what I said yesterday? You asked me this question. Sir, yesterday you told rating need not to take as base values. So on what basis here you have taken V1 rating as V base? See, already they have given the per unit numbers. As already they have given the per unit numbers, on what basis those per unit numbers are given? Definitely ratings as base values. I think you need not to rate these two statements. What's the statement I said earlier? It's not necessary to consider the ratings as base values while you are doing per unit calculation. But if already per unit calculations are given, per unit values are given to you, definitely those per unit values are on the base of ratings. Okay? Understood? Yeah. So let's say next advantage of using per unit quantities. See, actually, if you want to do analysis in the absolute domain, we need to deal with voltage, powers, currents, and all. Voltage in the sense it will be in kilovolts, thousands of volts, you can say. Power, mega, 10 power 6, 10 power 3. These terms you have. Doing calculations with this kilo, mega terminologies, it's a bit laborious process, definitely. Even hand calculations are a bit laborious, as well as computer calculations also laborious. But by using these per unit quantities, we are making that number maybe like 1, 0.5, 0.8. So magnitude of the number was reduced to a very, very low value, so that calculations will be a bit easy compared to the absolute domain. All of you getting my words, right? So the magnitudes of per unit numbers are very low or very less compared to absolute numbers. So calculations will be easy. Calculations will be easy. Calculations will be easy. Okay, calculations will be easy. Next advantage I am going to tell with respect to per unit quantities. So check the next advantage here. So I'm moving ahead to the next slide. Okay. So just look at my words, what I'm saying. We have two generators here which are not connected together, separate generators. It's a first generator G1, you say, showing the second generator here G2. Two generators have separate, not connected together. Ratings of first generator 10 kV, 50 MVA. First generator 10 kV, 50 MVA. Impedance of this generator ZG, it is J 1 ohms. J 1 ohm is a impedance of that generator. Next one. Second generator 20 kV, 100 MVA. 20 kV, 100 MVA. This generator impedance is also J1 ohms. Look at my words. Look at my words. Two generators I have taken separate. First generator ratings are 10 kV, 50 MVA. Second generator 20 kV, 100 MVA. First generator impedance J1 ohms. Second generator impedance J1 ohms. I am asking a silly question to you. Which generator is having more impedance? Which generator is having more impedance? Is it G1 or G2? Or both are having equal impedance? Which generator is having more impedance? Is it G1, G2, or both are having equal? How we can decide? See, both are having equal impedance. J1, that's okay. First one is having a rating of 10 kV, 50 MVA. Second one is having 20 kV, 100 MVA. But we can't compare these ohmic values directly, right? Because of unequal ratings. At that time, what you have to do? We should convert the first generator impedance into per unit domain, second generator impedance into per unit domain. Then only we have to do that comparison. Okay? Yeah. You attempt to find out ZG1 in per unit form. You attempt to find out ZG1 in per unit form. And you attempt to find out ZG2 in the per unit form. You try to calculate these per unit numbers. After that, we try to make that comparison. Calculate that by using formula. Try to calculate it. I'll come back within 1 minute. Please calculate that ZG1 and ZG2 in per unit. I'm really sorry. I'm really sorry. Please kindly excuse me. So ZG1 per unit we have to know, na? So obviously it is ZG1 in ohms by Z base. Okay. So what is ZG1 in ohms? J1. Okay. What is Z base? You know already it is V base. You assume it is single phase generator for easiness in the analysis. Single phase generator you assume it. Okay. So it is V base square by S base, na? So you can get 10K whole square in the numerator. By S base is 50 mega. So kilo square mega will be cancelled out. So it is J1 into 50 by 10 square is 100. So it will come to be J0.5 in per unit domain. J0.5 in per unit domain. What is Z02 per unit? So ZG2 per unit. ZG2 actual by Z base of the second generator. ZG2 actually is J1. What is Z base here? 20K whole square by 100 mega. 100 mega. So kilo square mega will be cancelled out. So J1 into 100 by 20 square means 400. And what is this number? J0.25 per unit. Means which generator is having more impedance now? Generator 1 is having more impedance compared to generator 2. All of you getting my words? Okay. So ZG1 is more compared to ZG2. That meaning actually, what is the thing we have to learn from this? What is the conclusion you have to make from this? ZG1 is more compared to ZG2. That's okay. What you have to learn is under rated operating condition. Under rated operating conditions, the voltage drop may be per unit. Per unit voltage drop in the generator 1 will be more compared to generator 2. That is a thing what we have to learn from this. Okay, simply current into impedance is the voltage drop. As a per unit impedance is more, per unit voltage drop is more, terminal voltage will be less for the G1 generator compared to G2 generator at the rated operating conditions. Okay, so if you want, I will write that statement also in the next slide. ZG2 per unit is greater, sorry, Z0, ZG1, generator 1 greater compared to ZG2 per unit. So comparing two apparatus is proper only in per unit domain. Is proper only in per unit domain. Only in per unit domain. Okay, we can't compare the absolute values directly. Okay, as I said earlier, that statement I am writing, ZG1 per unit is more compared to ZG2 per unit. That implies per unit voltage drop in G1 is more. G1 is more compared to G2. Compared to G2. G1 is more compared to G2. Okay, yeah. So next thing. Next advantage I want to tell, so-called third advantage. Third one, fourth one. Fourth advantage. Just observe what I am saying now. I will give one single line diagram to you along with the ratings. Along with the ratings of the equipment. We have generator connected to transformer 1. We have a line. One more transformer. And I have some load here. Okay, now I will keep the ratings of each and every equipment. First, transformer 1, 11 kV by 132 kV. Okay, second transformer, 130 kV by 6.6 kV. 130 kV by 6.6 kV. Ratings, not the operating voltage. Operating voltages might be different than the rated values. Okay, 11 kV by 132 first transformer. Second transformer 130 kV by 6.6 kV. You might be having a question that, sir, you said this winding is at 130 kV, this winding is at 130 kV. I am saying you again, these are rated values, not the operating voltages. Okay, but matched almost, right? 130 to 130, these are almost matched. For example, rather than 130, if I write here 60 kV, this is 132, then it may be a mistake. It may not be a proper connection. It may not be a proper connection. Generally, if you are interconnecting transformers together, similar voltage rating windings should be connected together. Similar rating windings must be connected together. See, if you see this secondary winding rating 130 kV, primary winding rating 130 kV, connected by a transmission line, it's a proper connection only. For example, rather than 130, if I take 60 kV, one winding, other nearby winding is 132, these two can't be connected by a transmission line. It's an improper connection. So I think all of you getting my point. Okay, yeah. So now at the present operating condition, it's a bus 1. I feel it's a bus 1. That bus 1 voltage is 10 kV. And I feel it's a bus 2. That bus 2 voltage is 7 kV. Bus 1 voltage 10 kV, bus 2 voltage is 7 kV. Bus 4 it is. You consider it as bus 4. Bus 4 voltage is 7 kV. Which bus voltage is high? Which node voltage is high? Is it the node 1 or node 4? Which node voltage is high? Anybody please tell me? Anybody please tell me? Node 1 or node 2? Node. It's not load. Node. Junction. Which node? 1 or 4? Okay. See, actually, node 1 or bus 1 voltage 10 and bus 4 voltage 7. It looks that V1 is greater compared to V4. But in between that, we have transformers, right? So if you have transformers in between those buses, it is not proper to compare the absolute voltages directly. We have to compare only per unit voltages. Okay? Yeah. So let me write. Comparing absolute voltages, absolute bus voltages, right, in the system consisting transformers is not proper. So this comparison must be done in per unit form only. Okay, right. So per unit form in the sense, listen please, listen kindly. Per unit form in the sense, you have to select some base value. Arbitrarily you can choose, that's your wish now. Arbitrarily you can choose. I will copy this diagram for the next slide. Okay, so I'm showing here. So I'm choosing base value. At this place. Kindly observe my words. Base value I selected here 11 kV. Interestedly I have selected base value 11 kV. Voltage 1. Actually, this base voltage is valid. Whatever you have selected 11 kV is valid up to the location of nearby transformer. Winding. After crossing the transformer winding, that base voltage has to be modified with the help of this transformation ratio. That's what we studied in the transformers. This transformer topic in the analysis. All of you getting my point? So this base voltage 11 kV is valid only up to this location. Beyond this point, base voltage has to be modified with the help of this transformation ratio. Okay, so what will happen to that base voltage now? Base voltage, base voltage ratio equals to voltage ratings ratio. So in this case, the voltage base will be equals to previous voltage base, this primary voltage base 11 into this transformation ratio 132 by 11. 11 will get cancelled out. It will be 132 kilovolts. So 132 kV is a base value here. How far it's valid again? On the transmission line, base voltage will be 130 kV only, and we have to continue means it will be extended up to the nearby transformer winding. Nearby transformer winding means up to this location, it will be valid to take this base value 130 kV. Beyond this transformer winding, again we have a transformation ratio. We have to change the base voltage according to the transformation ratio. Okay, see if you cross this, what will happen to the base voltage? Voltage base on this side equals to primary voltage base 132 multiplied with voltage 132 multiplied with ratio. What is that ratio? The location where you are calculating base voltage to the other means 6.6 by 130. 6.6 by 130. How many kilowatts is this number? 132 into 6.6 by 130. This number is 6.7. Almost you will get this number like 6.7 kilowatts. Okay, can you please tell me what is the value of V1 in per unit? V1. Logically, you have to think always. If you are writing one formula or if you are doing one calculation, it should be logically satisfied. At what bus you are standing now? Bus 1. What's the absolute voltage? 10 kV. We have to divide that absolute voltage with the base voltage. What base you have to take? Bus 1 base. You should consider base voltage at which location? Bus 1. What is the bus 1 voltage? Base. 11 kV you have taken. 11 kV you have taken. So it will be 10 by 11. 10 by 11. That's the value of V1 in per unit domain. Okay. What is V4 value in the per unit domain? What is the absolute value of V4? 7 kV. Okay. What is the base at this location? What is the base at that fourth bus location? That is 6.7 kV. So 7 by 6.7, that is the value of V4 in per unit. Following all of you, right? So let me write that V1 value in the per unit domain. Actual value 10, base is 11. You write V base at bus 1. V base at bus 1. And V4 per unit value, actual number 7, base is 6.7. So 6.7, it's the V base at bus number 4. Okay, you calculate these values. How much you will get? First bus voltage 10 by 11. So it will be 0.9091. You can write 0.9091. Second value 7 by 6.7. So it will be 1.0447 means 45. So from this, you can call definitely V4 value in per unit form greater compared to V1 per unit. So comparing voltages is proper only in the per unit domain in this type of system. Anybody having a doubt? All of you getting my words? Very clear, very clear. Wherever you want to calculate the per unit quantity, at which bus you want to calculate. With respect to that location, base only we have to consider. That location base value only we have to consider. Okay. Sometime maybe after this, obviously we study something like common base and all. Okay. Yeah, simple. Swastik. Satvik. Look here, V4. Absolute value I have given 7 kV. Present operating voltage is 7 kV. What is the base voltage at the bus 4? Base voltage at the bus 4. I calculated just now by considering common base at this location. How much is base voltage? 6.7. Means what is the per unit voltage at the bus 4? Absolute voltage at the bus 4 by base voltage what you have considered at that location. 6.7. So 7 by 6.7, that is a per unit voltage at the bus number 4. Okay, I think all of you understood this. So what is the base voltage at 130 kV? Obviously 132, right? Sanjay Kumar, what is the base voltage at this bus bar? What's the base voltage at this bus? 130 kV, right? Base voltage, look here. In this complete zone, what this term? 1 minute, please. Yeah, see, this one, for this complete zone, base voltage will be 130 kV only. For example, if you want to calculate line reactance in per unit domain, what's the base voltage? 132 kV we have to consider. Following. And for this zone, generator and this primary winding of transformer as a whole, what's the base? 11 kV. What's the base of this one? Generator, transformer, secondary, and then load as a whole, base voltage is 6.7 kV. Like that, you have to understand. If absolute values are not given in the question, then we take ratings of transformers. No, Venkana, no. Why 10 is taken instead of 11? I am giving the bus voltage. Bus 1 operating voltage 10 kV I have given. Bus 4 operating voltage I have given 7 kV at the present loading condition. Okay. Yeah. The next topic what we are going to discuss here is per phase impedance diagram construction. See, already at the beginning stage of this chapter, we have seen how to represent generator, transformer, transmission line in the per phase model, connecting them and building up a per phase network. Okay. Same discussion I am going to do now, but in the per unit domain. Okay. Per unit, per phase impedance diagram construction. What are the various steps to be followed? That we'll discuss first. Later on, we will think about some problems on the per phase impedance diagram construction. Okay, so the next heading is per unit, per phase, impedance, network construction. Network construction. Per unit, per phase impedance network construction. Okay, steps to be followed. Steps to be followed. Follow. Step number 1. Listen carefully. Listen carefully. Step number 1. First, you have to consider the common base. Common base values you have to select at some location, wherever it is. It may be at some generator location or at some transmission line, whatever. Okay? Yeah, you see. Select the common base value. Base values at certain location. Certain location. Select the common base values at certain location. Common base values means what? One is a voltage base. Second one is a S base. I said earlier, at least 2 base values has to be considered. I am selecting voltage base and the S base for easiness in the calculations. Okay. So, in bracket, common voltage base has to be selected, common S base has to be selected. S base has to be selected. Okay. See, listen here. I'm asking one very, very simple question. Sir, V base gets changes with respect to location. Then what happens to S base? I'll come to that. Yeah, listen please, listen. I'm asking one very silly question. I'm moving to next slide just to do some rough work. I have one generator. Rating of this generator, ratings of this generator, 11 kV, 150 MVA. These are ratings of the generator. 11 kV, 150 MVA. What will be the base values we have to select? In the exam, if you talk in the view of exam, in the exam, if they have not mentioned anything regarding base in the problem, if they have not mentioned anything regarding the base value in the problem, choice is given to you to select any number. What value I will select? Base voltage you tell me. Voltage. Can I select 11 kV? That's my choice. Can I select 11 kV? Yes or no? Tell me. Can I select 11 kV? Yes. Can I select 110 kV? Base. Can I select 110 kV as a base? Yes or no? Yes. Can I select 1 kV as a base? Can I select 1100 kV as a base? That's your choice. You can choose any one of these numbers as a base. you convert the values into per unit form. But if you are converting those per unit values back into absolute, you should multiply with the respective base what you have selected. That's a logical way of thinking actually. First we selected some base, we converted the value into per unit form, we done the calculation. Whichever the result we got in per unit form, that we have to convert back into absolute form with the base value what you have selected. Then obviously absolute value will be remain same. Absolute value will be remain same. Whatever the base you select in the calculations. Yeah. All of you getting my point? Please tell me. Please tell me. Yes or no? If you select 1 kV base, obviously that's what? That common sense you have to use now. That common sense you have to use. Which base we have to select? 11 kV, 110 kV, 1 kV, 1100 kV, which will give less calculations to you. Less calculations that you select. That's your common sense. But one suggestion made by the people is try to select rating of the apparatus, voltage rating of the apparatus itself as a common base at that particular location. That is a suggestion made by the people. Anyhow, I'll write first here V base, voltage base, can be selected any value. Can be selected any value. Can be selected any value. But suggestion is choose voltage rating of apparatus as base value. Base value at which you are standing, of course, at which apparatus location you are standing, that you select as a base value. That's a suggestion made by the people, but we will follow it. Most of the times we will follow it. Okay, what's the S base you have to select? S base. Yeah, if you choose 0 kV as a base, why you are asking this unnecessary questions, Mr. Anonymous attendee? 0 kV will give even less. If you choose 0 kV as a base, how much is your per unit voltage? It will become infinite, right? Absolute value by 0, infinite. Listen to this. S base. What value you have to select as S base? Again, choice is yours. You can choose either 150 MVA, whatever the rating given, or you choose 100 MVA, 1500 MVA, 15,000 MVA, whatever the number you want, you can select. Okay, so S base, I'll write here. I think I can remove this. Else I'll write S base. Can be selected any value. But one suggestion is you try to select the S base value as highest rating of any apparatus. Highest power rating of any apparatus. That's a suggestion only. If it is required, you follow, else you can avoid it. No issue. Suggestion. But in the exam or in the question, if they have given the base value, then there is no issue with that. Okay? Suggestion. Select highest S rating, apparent power rating of any apparatus. As base. As base. That's a suggestion given by the people. Okay, done. Next thing, after selecting common base value at certain location, immediately what you have to do is we should use a transformation ratio of transformers, and you should transfer the base values from one side of transformer to other side of transformer. By that way, we have to give the base values at all the apparatus, in the system. Okay, yeah. So second step in the per phase impedance diagram construction, that is calculate common base values, at all apparatus locations, by using transformation ratios of transformers. Okay, so after calculating common base values at all apparatus locations, sometimes they might give per unit value of each apparatus impedance, maybe by choosing ratings as old base values. Else, we will do that in problem. Simply what I will write the next step is calculate per unit impedance of each and every apparatus on this common base selected. Okay, we'll do in problem. Third step, calculate per unit impedance values of each apparatus in the system. On common base. On the common base. Okay. So after doing this one, in the next step, connect or replace each apparatus with its per phase equivalent circuit in the per unit domain. Connect those per phase equivalent circuits according to the single line diagram given. Replace each apparatus with its per phase equivalent circuit and connect them according to the single line diagram given. SLD. Single line diagram given. According to single line diagram given, we have to connect them in a proper way. That will be the per phase per unit impedance diagram. Yeah. Done. So I'll wait for 5 seconds. Please complete it quickly. We'll go with some problems here. So I think I can move. Okay. So I'm taking some problems here. So this is a previous GATE examination question. So it's a question. I will give options to you. It's from classroom objective questions. It's from the classroom objective questions. So it's option A. Remaining options. Okay. So I'll show these options in the next slide. Yeah. So please go through this question. For the power system shown in the figure, previous gate question it is. Previous gate examination question. I think asked in 2010. Yeah. For the power system shown in the figure below, the specifications of the components are following. G1, generator 1, 25 kV, 100 MVA, X equals to 9%. I said you already, don't do the calculations in percentage form, do the calculations only per unit. We have to write this number 0.09. Generator 2, 25 kV, 100 MVA, X value 9%. T1, first transformer, 25 by 220, 90 MVA, X value 12%. Similarly, T2 also. Line 1, only one line we have, that line, 220 kV rated voltage line. Line rated voltage is 220 kV, that's okay. The X value 150 ohm. They have given directly this in ohms, not in per unit. Next, choose 25 kV as a base voltage at the generator 1. The generator 1, you should select the base voltage as 25 kV. And 200 MVA as a MVA base. 200 MVA as MVA base. The impedance diagram is, they have given 4 options here. 4 options. We have to select one among these 4 options. Okay? Yeah. So simply, I will redraw the single line diagram first. I will keep all the ratings, whatever they have given for each and every apparatus on the diagram. As it's the first problem, let me discuss a bit in detail. Just from the problem given, we have generator 1 here. Transformer 1. We have this as line 1. Transformer 2. And here we have one more generator, G2. G1, G2, T1, T2, line 1. Keep the ratings. Generator 1 rating, 25 kV, 100 MVA. Generator 1 rating, 25 kV, 100 MVA. T1 transformer, 25 kV primary, 220 kV secondary. Rating is 90 MVA. Rating is 90 MVA. Line 220 kV. Just listen to my words. Listen. Line 220 kV. It is connected to nearby 220 kV transformer winding. That's perfect. Other side of the line, winding, transformer winding must be rated to 220 kV or close to 220 kV. Okay. What are the T2 ratings given? T2 ratings, 220 kV by 25 kV means this side, line side must be 220 kV winding. Other side will come 25 kV winding. Rating 90 MVA. Voltage rating is 90, power rating is 90 MVA. G2, generator G2, 25 kV, 100 MVA. Generator G2, 25 kV, 100 MVA. Okay, fine. What are the base values he is asking us to select? One more thing I want to tell. Listen here, all of you listen here. What are the old base values for you? Ratings itself as old base. Whatever the ratings they have given in the problem, those values itself are the old base values. Means, whatever the reactances given in the data are in per unit form on the basis of old base or on the basis of their ratings. Okay, now, what is a new base value he is asking us to select? 25 kV base voltage, 200 MVA base MVA at what location? G1 location. Okay, so at the G1 location, common base or new base, you can say. I am writing this with the red color. 25 kV, 200 MVA. 25 kV, 200 MVA. You know, this common base values what you selected, 25 kV, 200 MVA, valid up to nearby transformer winding. Why? Why it is valid up to only nearby transformer winding? Because after crossing the transformer, voltage base value will be modified according to the transformation ratio. That's why we say it is valid up to winding, nearby winding of transformer. Okay. On the other side, new base value will be, how is a base MVA? How is a base MVA? Remains same. Because transformer primary side MVA base, secondary side MVA base, both are equal. So S base at this location will be remain same at 200. But there is a change in the voltage base. What is that new voltage base? Means modified voltage base onto the line side. Primary side 25 kV base multiplied with transformation ratio 220 by 25. So 25 will be cancelled. You will get this number as 220 kV. And these base values are valid up to nearby transformer winding. Maybe up to this location it is valid. Okay, from other side, on the other side of winding, what will happen to the new base value? S base will be remain same, 200 only. It won't change. S base will be remain same, 200 only. And what will happen to voltage base value? Voltage base. Primary side voltage base is 220. Transformation ratio 25 by 220. 220 gets cancelled out and it will result into 25 kilowatts. 25 kilowatts. Getting now we know the new base value at each and every apparatus location. Next, we have to calculate per unit impedance of each and every apparatus on this new base. Okay. First, you do for generator 1. Generator 1. Look here. Generator 1. G1. What is the reactance of generator 1 given in the data? What is the reactance of generator 1 given in the data? 0.09 per unit. That's on which base? 25 kV, 100 MVA. What is the new base at G1? What is the new base at G1? 25 kV at 200 MVA. Any change? Yes. Base MVA was changed. 100 MVA, 200 MVA. So there is a change in the reactance of the G1 generator. Okay. So again, I am saying, as it was the first problem, let me write old base, 25 kV, 100 MVA. Okay, new base values, new base, 25 kV, 200 MVA, and you know XG1 old 0.09 per unit. What is the value of XG1 new? XG1 per unit new number. XG1 per unit new number. You no need to write the formula. If you have remembered, that's fine. Just if you want to write formula once. Z per unit new equals to Z per unit volt into V base volt by V base new whole square into S base new by S base volt. Okay, that formula I will write only once here. Z per unit new formula. Z per unit volt into V base volt by V base new whole square. V base volt by V base new whole square. S base new by S base old. S base new by S base old. Only once I have written. Let's proceed with the calculations. XG1 per unit new. Old value. So V base old by V base new means 25 by 25 whole square. That will be 1, of course. S base new 200. S base old is 100. So this number is 0.18 per unit. Means reactance of generator is 0.18. Impedance means J0.18. Let's look at the options once. Let's look at the options. Two options are having that. Option A, J0.18. Option B also J0.18. So our answer might be any one among these two, either A or B. Let's compare these two options now. J0.27, J0.42, J0.62. Means to get the correct option between these two, if you calculate the transmission line impedance in per unit form, if it is coming as 0.42, your option will be A. If it's coming as 0.62, your option will be B, obviously. All of you getting my point? That's a way of elimination, actually. But as it's the first problem, Let's do all operands. Okay, T1 transformer I want to do now. First transformer T1 transformer. It's a small confusion, but it's simple only. Listen, T1 transformer. Which side you want to do the calculation, that you decide. Do you want to do the calculation on the primary side or on the secondary side? That you decide first. Decide. Which side you want to do calculation? Primary or secondary? Which one? Primary, let us do. Primary. If you are doing on primary, old base values, new base values, we should select on the primary side only. What is the old base on the primary? 25 kV, 90 MVA. What's the new base on the primary? 25 kV, 200 MVA. That's it. You do that calculation if you want. Else, if you want to do the calculation from secondary side, what's the old base on secondary? Old base on secondary, 220 kV, 90 MVA. Old base on secondary, 220 kV, 90 MVA. New base on secondary, 220 kV, 200 MVA. Any one you have to follow. Understanding? You should not do both. It is not required to do both calculations. You do any one that will give the per unit impedance on the new base. Let's do on secondary side. Secondary side, old base. Secondary side, old base. 220 kV voltage base. Power base is 90 MVA. Secondary side, new base, you have to consider. Secondary side only we should take. 220 kV, 200 MVA. Okay. What is transformer reactance in per unit form? Old base. On old base, transformer 1 reactance is 12%. Means it is 0.1. This number is 0.1 per unit. Now, what is that XT1 per unit new? XT1 per unit new. Old value into V base old by V base new. V base old by V base new whole square into S base new by S base old. So 200 by 90. You calculate this value in per unit form. How much? 0.12 into 200 by 90. This number is 0.266 or 27. 0.27 per unit. That's a transformer 1. Transformer 1 per unit impedance. Okay. Again, some people may get a doubt. Listen, please, listen. Some people may get a doubt. Sir, you said it is V base old by V base new whole square. S base new by S base old. What base values I have to consider? Whether these are per phase or line to line 3 phase. That's your wish. For example, if you take per phase, V base old 220 by root 3. V base new 220 by root 3. Root 3 cancelled out. 200 by 3, 90 by 3. By 3 by 3 cancelled out. Same number you get. Okay. If you are taking line to line old base, you consider line to line new base. If you are considering 3 phase old base, 3 phase new base. You should follow that logic. Okay. So old base I will take per phase, new base I will take line to line. It's not a suitable one. Obviously, it's not logical to say. Okay. So if you are taking line to line voltage base and 3 phase MVA base as a old base values, new base values also you should consider in a similar manner. Done. Next, line will do now. Transmission line. See, transmission line, you see, directly line 150 ohms is a XL 150 ohms. Directly absolute value was given. So you no need to bother about the old base numbers. Simply this absolute value you divide with the Z base with the help of this new base values. Okay. Yeah. Let's move ahead to the line. Base values on the line. Of course, new. Base values on the line. 220 kV line to line voltage base. 200 MVA 3 phase apparent power base. 3 phase apparent power base. And what's the Z base value we can find? Of course, it is Z base per phase. There is no doubt about it. Z base per phase. What's the formula? V base per phase square by S base 3 phase. Else, you can write V base line to line square by S base 3 phase. Because both will give same number. That's why I'm writing this one as V base line to line square by S base 3 phase. It's a Z base per phase. Okay. Yeah. So simply you substitute those numbers. 220 square in the numerator, denominator 200. You see numerator kilo square, denominator mega. Kilo square mega will be cancelled out. So it will come in unitless 220 square by 200. So this number is 242 ohms. 242 ohms. So per unit value of that line reactance will be XL by Z base. So 150 by 242 we have to take. So XL actual is given 150 ohms. XL per unit is XL actual by Z base. XL actual is 150. Z base is 242. Calculate this number 150 by 240. 0.6198 means it is 0.62 per unit. 0.62 per unit. Okay, 0.62 per unit. So 0.62 is there in one of the option. Let me check the options here. 0.62 we have in the option B. So your answer is option B. Option B. Okay, let's do remaining also a bit quickly. Second, next transformer, you have to do the calculation. T2 transformer, simple. T2 transformer. Which side you want to consider? Primary side or secondary side? Anybody? Let's do on secondary for T2. What are the old base on secondary? Old base on secondary. 25 kV, 90 MVA. 25 kV, 90 MVA is a old base on secondary. New base on secondary. 25 kV, 200 MVA. There is a change. We have to calculate that number. T2. T2. Secondary side old base. Secondary side old base. 25 kV line to line. 90 MVA. Secondary side new base. We have that number. 25 kV, 200 MVA. 200 MVA. What's that transformer 2 reactance? 0. I think 12. Let me check once. Data 12. Okay. 12. So XT2 per unit new we will write now. So I'm moving to the next slide. XT2 per unit new number. Old per unit value 0.12. Base 25 by 25 base voltages. Kilo gets cancelled. MVA base new 200. Old MVA base is 90. So if you calculate this number, you may get again 0.27 per unit. So T1 and T2 transformers are identical. Old base values and new base values are same. So you get the same number 0.27. Okay. So at last we say for generator G2. Generator G2, that's the next element what you find there. Old base 25 kV 100 MVA, new base 25 kV 200 MVA. Old base 25 kV 100 MVA, new base 25 kV 200 MVA. 200 MVA base. Okay. And generator reactance old value, it is 0.09. If you want to check the data, check the data in the question. 0.09. And how much is that XG2 per unit new? XG2 per unit old value into kV base old by kV base new whole square, MVA base new by MVA base old. So this number will come to be 0.18 per unit. Generator 2 per unit reactance is 0.18. Now you draw that equivalent circuit. per phase equivalent circuit by replacing each and every apparatus with its per phase equivalent model. Okay, yeah. So let's take in the next slide. Why S dash value remains same? It's coming Vedant. What I have to do? Vedant Chartal, S base value, it's coming as same. How in the sense? Transformer, even though you are using the transformation ratio, S base is not changing. So one of the conclusion you can make here if you want, one of the conclusion we can make here if you want, if you select the apparent power base value at some place, definitely at all the places in the system, S base will be remains same number. Only voltage base value will change according to transformation ratio of the transformers. Okay, yeah. So let's move. So per phase impedance diagram, I'll say per phase impedance diagram. First generator one, transformer one. If you want, you look back to the single line diagram. Look back to single line diagram. First generator one, right? So like this, I'm keeping generator one equivalent circuit. It's a neutral. It is some voltage source. Doesn't matter. Generator one per unit impedance. It's a bus one you take if you want. Bus one. Next we have a transformer T1. In the per unit domain, it is represented simple series impedance by removing the coupled circuit. Represented as a simple series impedance by removing the coupled circuit. It's a ZT1 per unit. Bus 2 to bus 3, transmission line, it's a simple series impedance. Bus 2 to bus 3, line with an impedance of ZL. So I'll call it's a G1, E1 transformer, transmission line. Okay, bus 3 to bus 4, you have a transformer. Again, it's going to be represented as a series impedance. It is transformer ZT2. Bus 3 to bus 4, it will be represented as a transformer series impedance ZT2. At bus 4, you have a generator. It is going to be represented in this manner. Second generator, G2. Should keep in this way, G2 generator. And this is some voltage source. And this impedance is ZG2. Okay, let's keep these numbers quickly. Generator 1 per unit impedance new on the common base, J0.18. 0.18 is the reactance of the generator per unit. 0.18 is the reactance of generator. Impedance of generator means J0.18 you should write. That J term is very costly. Okay, you should not miss that J. If you miss that J, there is a chance of committing the mistake. Okay, yeah. Next, T1 transformer, reactance is 0.27, impedance means J0.27. Transmission line, you calculated the numbers that I am recalling without going to the previous slides. Line, reactance is 0.62, impedance is J0.62. Second transformer impedance J0.27, generator 2 impedance J0.18. So according to the options given, we said the option already B. We said that correct option is B. I said already, you can go. Yeah, Shamala, I said in the yesterday class itself, any three-phase apparatus, rated voltage will be always in the form of line-to-line value. Any three-phase apparatus, power rating will be mentioned in the form of three-phase. If you want, I will write that statement. I will come back to the problem. Somebody has a doubt, I want to clear this one. Rated voltage of three-phase power apparatus power apparatus will be always represented as line to line RMS value, irrespective of the name of the apparatus. Either it is generator, transformer, line, whatever it is. A transmission line, three-phase line rated for 220 kV. What's the meaning of that? 220 kV line to line RMS value is the rated voltage. Okay, so the rated apparent power of three-phase power apparatus will be always represented as three-phase value. It's not per phase, it's a three-phase value. Okay. Whatever it is, in case of star, delta, whatever it is, line to line voltage, that's it. Line to line voltage. Line to line voltage. I said it's a line to line voltage. That's it. Why you are getting a doubt again, delta star? Shamla, you may be clear with your doubt. Maybe if I go to the next problems, where I will discuss about star delta something. Okay, come back to the problem here. So this answer, just check the options, what they have given. I said option B is a correct one. Okay, can anybody tell me a correct answer I need from the discussions what we have done? Correct answer. What is this generator 1 voltage, internal EMF EG1? What is this generator 2 internal EMF EG2? What is EG1 value in the per unit form? What is EG2 value in the per unit form? I need a perfect answer. Per unit I need. How you say 1 per unit? All are saying 1 per unit. How come you say 1 per unit? How come you say EG1 equals to 1 per unit? How you have taken it? Anybody? By considering 25 kV as operating voltage, how you assume it? Rated voltage 25 kV may not be operating voltage, right? Rated voltage of the generator 1 is 25 kV. It may not be operating voltage. Then EG1 value I can't say as 1 per unit. EG2 I can't say it as 1 per unit. If you provide some more data, maybe current flow in the system or some other data if you provide, then only I can say what is the value of EG1 and EG2 in the per unit domain. All of you getting this logic? All of you getting this one? Sir, it's going to be less than 1 per unit. I can't say Bharat. How I can say it's less than 1 per unit? I can't say. Apply KVL, Nitish Reddy, that's perfect. Apply KVL. But in the application of KVL, at least we should know EG2 to calculate EG1. Yes or no? And you have to know current flow in the system. Definitely. Yes. If the data is given, we are comfortable to calculate EG1, EG2 and any bus voltage in the system. Okay, fine. So it is a per phase equivalent circuit which can be used. If we ask in this, then how? That's why Charan Reddy, they are very clear in their question. They didn't mention the values of voltages of the generators. Yes or no? They have not mentioned the voltages of the generators. That's why I ask you to follow the previous gate questions thoroughly, rather than following some other questions. So considering the voltages base also, generator new bases, we are getting same answers. Yeah, Muthiredi Vasista, in the question, if they have given the new base value, how you deviate your answer? If they have given the new base values in the question, then how you choose your own base values? You should not select it, right? Because whatever the per unit impedance diagram is giving in the answer, that is according to the new base values given in the question. You should not select your new base values on your own way as they have given in the problem. Getting me? Okay. Yeah, next. So let's take one more problem. One more simple problem I want to take up quickly. Yeah, go through this one. Okay, it's a very simple question that you can answer. I'm not discussing it. I will give that as a homework to you. Let's do it. Take up this question. Read that. Go through this. In the figure shown below, the rating, below, a generator was synchronized to infinite bus bar. Generator was connected to infinite bus bar. That's it, sufficient. Ratings of each equipment are mentioned below. 60 MVA, 12 kV, XD equals to 0.5 per unit. Okay. Transformers each, T1, T2, both transformers. 80 MVA, I'm really sorry, it's not 12 kV, it's 11 kV. 11 kV. Okay. 80 MVA, 11 kV by 66 kV, comma XT equals to 0.08 per unit. Line, reactance 12 ohms, resistance is negligible. Draw the per unit impedance diagram by choosing base values as 100 MVA, comma 66 kV at appropriate location. At the appropriate location, you should select the base values as 100 MVA, comma 66. Means these are the new base values you should select at some place. And you have to draw per unit impedance diagram of this. Okay. Why per unit AG1 is not less than 1 per unit? Varshasri, why can't it be? Why can't it be more than 1 per unit? Why can't it be equal to per unit? Why can't it be less than 1 per unit? We can't say. That's what I'm saying, Varshasri. I can't say. It may be less than 1, more than 1. I don't know. Yeah, 105. I am showing. Somebody asked me to show 105. Slide number 105. Let's move to present slide. Okay. First, I will draw this single line diagram. I'll keep the ratings of each equipment on the head of this diagram. After that, we select the new base under. So I'm copying the same diagram what we have here. The solution. Okay. So I'm keeping ratings of these equipment. Ratings. Generator rating 12 kV 60 MVA. Ratings 12 kV 60 MVA. Okay, next. Transformer T1. Kindly listen my words. Listen all of you. Listen all of you. Listen. Power rating 80 MVA. I'll keep 80 MVA here. You see, transformer T1 voltage rating is 11 kV by 66 kV. 11 kV by 66 kV. So one winding rated for 11 kV, other winding rated for 66. Which winding we should take 11? Which winding we should take 66? That's the question. See, if you see, primary winding connected to generator. Primary winding connected to generator. What's the generator rated voltage? 12 kV. Means primary winding rated voltage should be close to 12. Should be close to 12. So close to 12 means we can choose 11. So primary winding rated voltage, you can take 11. Other voltage will come 66. Means obviously your line rated voltage will be 66 kV. Line rated voltage will be 66 kV. Next, listen. This is a place where you get it out. If the line rated voltage is 66 kV, the connected winding to the line means this winding, T2 primary, This winding voltage, rated voltage, should be close to 66. This winding rated voltage should be close to 66. But already I said both transformers are identical, having a ratio of 11 by 66. Means 66 kV winding I should consider as a primary here, 11 kV as a secondary. That's a way of considering the ratings in a proper order. And of course, this power rating is 80 MVA. On both sides, it is 80. Both sides, it is 80. Anybody having doubt here? Anybody having doubt? All of you understood this? Very simple. How to select the winding rating is nearby apparatus you should check. Line is rated for 66. This winding voltage should be close to rated voltage should be close to 66. I have rating as 66. I have taken that. Other winding will come 11 kV. Okay, now base values. Yeah, star delta you don't bother, Sunil. Sunil, you don't bother. You don't bother, right? About this, that star and delta. I will come to your doubt if you have any. Just listen, just listen. Per unit impedance diagram by choosing base values as 100 MVA 66 kV. Na? Which location you should consider this? 100 MVA 66 kV. What we have to match with the ratings of apparatus given here. Voltage base you should match. Because I said one suggestion already, voltage base value generally taken close to the rating of the apparatus. That's why 66 kV is a voltage base given. Which apparatus is having 66 kV voltage rating? Transmission line, safest one. Safest one is transmission line. Means whatever the base value is given here, these base values might be on the transmission line. Okay, if you want, I will write the statement in the next slide. New base values, base voltage is 66 kV. Of course, it is line to line. Of course, it is line to line, three-phase system. 66 kV, line to line. New base voltage is 66 kV. So this base voltage matches with rating of transmission line. Rating of transmission line. This base voltage matches with the rating of transmission line. That implies the new base values might be given on transmission line location. Given on transmission line location. Okay? Transmission line location. So I can choose here common base 66 kV 100 MVA. It's a new base. Up to what extent these base values are valid? Nearby transformer windings only. Because after crossing that, base voltages will change, but MVA base remains same. Okay, so that's valid up to this location, and that's valid up to this location. After crossing this, base MVA remains same, 100, new base, right? 100 MVA. What will happen to voltage base? Voltage base value will be modified like this. 66 on the other side, base voltage into ratio 11/66. So it will come to be 11 kV. So on the generator, new base values are 11 kV, 100 MVA. 11 kV, 100 MVA. Okay. Next, on this side, new base. MVA base as it is 100. MVA base will be as it is 100, but voltage base will change. You have to identify 66 on the other side into 11/66. 11/66. It will come to be 11 kV. Means new base values on the infinite bus side, 11 kV, 100 MVA we have to consider. 11 kV, 100 MVA you have to consider. I will discuss that infinite bus, Teja. I will discuss about that infinite bus. That is also one of the intention of this problem, to discuss about this infinite bus. Okay. Next, immediately what we do is we try to calculate the per unit impedances, new per unit impedances on that new base value. First generator, new base 11 kV 100 MVA, old base 12 kV 60 MVA. There is a change. There is a change. Definitely generator reactance we should modify to new number. First generator we are taking up. Old base values means ratings only. 12 kV 60 MVA. Generator reactance, how much? Generator reactance is 0.5. D means direct axis. D in the sense direct axis. We'll come to know as we proceed further. 0.5 per unit is this number. 0.5 per unit. Now, new base values are 11 kV, 100 MVA. So, Xg per unit new we have to calculate. Xg per unit new. Already I have written the formula. Xg per unit old into V base old by V base new whole square. V base old by V base new whole square means 12 by 11. Multiplied with S base new by S base old, 100 by 60. S base new by S base old, 100 by 60. Yeah. So you try to get this number how much? 0.5, 12 by 11 whole square, 100 by 60. So it is 0.9917. 0.9917 per unit. 0.9917 per unit. That's a Xg per unit new. Generator reactance per unit new value. Okay, next T1 transformer. T1. Which side you want me to do? Or which side you want me to take the calculations? LV side or HV side? Anybody please tell me. Which side? LV or HV? Let's take on LV side. LV side. LV side means primary now. What's the old base? 11 kV 80 MVA. 11 kV 80 MVA. What's the new base on LV side? 11 kV 100 MVA. If you want to do on HV side, old base 66 kV 80 MVA, new base 66 kV 100 MVA. Okay, right. So transformer T1, primary side old base 11 kV, 80 MVA. Transformer reactance is how much? I think it's 0.08 per unit. Either referring to primary or referring to secondary per unit. Primary side new base. New base 11 kV 100 MVA. So that XT1 per unit new equals to XT1 per unit old into V base old by V base new whole square, S base new by S base old. S base new by S base old. You calculate this number, you get this as 0.1 per unit. You get that as 0.1 per unit. Transformer 1. Next, transmission line. Transmission line. Let's look at this line. Base value 66 kV 100 MVA new. Line reactance is given 12 ohms. Absolute value itself, you know, that you have to convert into per unit form. So T1 transformer was over. We are doing for line. Line. Base values on the line. Of course, new base values on the line. 66 kV 100 MVA. Reactance of transmission line is 12 ohms. Okay, you calculate Z base based on these values. Z base per phase or Z base sorry, Z base per phase means V base per phase square by S base per phase. Else V base line to line square by S base 3 phase. Anything you can write? You write if you want this formula. V base per phase square by S base per phase. V base per phase means 66 by root 3. We should write kilo square. Kilo square in the numerator. Denominator mega will be cancelled out. 1 by root 3 square, 1 by 3 also cancelled out. So 66 kilo whole square by 100 mega. That's it. Line to line voltage base square by MVA base 3. So it is 66 square by 100. So this number will be 43.56. Now you can write XL in per unit form. Actual value 12 by base value 43.56. So it's 12 by 43.56. So this number is 0.2755 per unit. Transmission line. Okay, why the new base is 66 kV? That's what he said in the problem, right? That's what he said in the problem. He said base values in the problem already. Yes or no? Rohit. Yeah. Next, after doing for line, next equipment T2, if you do for T2, it will come same as T1. If you want to check, LV side you take old base 11 kV 80 MVA, new base 11 kV 100 MVA. Okay, but T1 also coming as same. So T2 transformer reactance will be coming as same as T2. So T1. So if you want to write T1 transformer, so T2 transformer, I am writing directly XT2 per unit new will come same as XT1 per unit new. By calculations only I am saying it will be 0.1 per unit. 0.1 per unit. So we got the reactances of all equipment here. What about star delta? Listen here, listen. Look, all of you. What you do with that star delta? What's the doubt you have with that star delta? For example, T1 transformer, we have taken on LV side. Delta, very good. Delta. Okay. What is the volt base on the primary? 11 kV 80 MVA. 11 kV 80 MVA. What's the new base on the primary? 11 kV 100 MVA. Okay. See, T1. Listen here, listen. Z per unit new formula, that is Z per unit volt into V base volt by V base new whole square, V base volt by V base new whole square into S base new by S base old. S base new by S base old. Okay, listen to me. Primary side, listen. Whatever the doubt you have, I will clear it. Primary side, volt base value 11 kV 80 MVA. Primary side, volt base values are 11 kV 80 MVA. What do you want to consider that 11 kV? What do you want to consider that 11 kV? Do you want me to take that as line to line or per phase? You tell me your option, Mr. Bhaskar, Rajdurai. Bhaskar and Rajdurai, please tell me what you want me to consider that 11 kV. Is it per phase or line to line? Tell me your answer, please. Per phase you want me to consider? Per phase. Okay. So V base per phase, volt value 11 kV. What is the S base per phase volt value? S base per phase volt value 80 by 3. Because it's delta, na? Delta, line to line voltage and per phase voltage will be equal. Good. What are the new base values now? What's the V base per phase mu? That will be 11 only, right? 11 only, yes or no? If you feel this as a winding voltage applied, that will be obviously 11 base. And what is the mu S base per phase? 100 by 3. 100 by 3. S base per phase mu is 100 by 3. Substitute the numbers, you get same, right? Then why you are bothering about the delta star conversions, sorry, connections and all? Substitute these values in this formula, you will get same number. Both are same. Have you understood, Bhaskar? Bhaskar, have you understood this? So while you are applying this formula to calculate Z per unit mu, while you are applying this formula in the calculation of Z per unit mu, you no need to bother about the connection is either delta or star. No need to bother whether the connection is in delta or star. You no need to think about it. Getting? So there's always ratios of old and new bases of it may not be. Then we can have different result. How we can get different result? Jitendra, substitute the values and check the number. Are you getting different value or same? Transformer 2 also you calculate Hema. It will come same number. Transformer 2 also if you want. You calculate, you get the same number. Sir, if line side delta, then there the line per unit impedance will be different now. Say anonymous attendee, and all of you, of course, all of you, just listen to this one. Just I'm doing some rough work here. Listen, all of you, listen. Yeah, I'm discussing that Jitendra, not only for Jitendra, for all I am saying here. Kindly listen, kindly listen. So I have a star delta transformer now. Star delta transformer. Observe. Star primary. Okay, delta secondary. Star delta transformer means it is star primary, delta secondary. You should not get this doubt again and again. That's why I'm discussing this one. It is transmission line wire. Transmission line. Okay, next. Listen. Ratings of this transformer I'm giving. Ratings. Primary, I'll say 400 kV primary. Secondary 220 kV. Primary 400 kV, secondary 220 kV. Just nameplate on the nameplate. What do you mean by 400 kV? Is it line to line or per phase? Tell me. What do you mean by 400 kV? Is it line to line or per phase? Line to line. Just rating, na? Rating means it's a line to line only, right? Line to line rated voltage. What is 220 kV? That's also line to line rated voltage. That's it. Means what you have to understand here is primary side line to line rated voltage is 400 kV. Primary side line to line rated voltage is 400 kV. What is secondary side line to line rated voltage? Secondary side line to line rated voltage is 220 kV. Are you clear? Secondary side line to line rated voltage is 220 kV. Primary side line to line voltage is 400 kV. Clear? Next one. What is the rated voltage of winding on the primary side? What is the rated voltage of the winding on the primary side? 400 by root 3 because it is star. Line to line voltage 400, per phase voltage 400 by root 3. Rated voltage. 400 by root 3 kilovolts. Okay. What is the rated voltage of winding on the secondary side? Rated voltage of the winding on the secondary side. Anybody please tell me what is the rated voltage on the secondary side? 220, because it's a delta winding, line to line and phase winding voltages are equal. 220 kV. Okay. Can anybody tell me, particularly with respect to transmission line I am talking, particularly with respect to transmission line wire I am talking. If I am asking you, what is a conductor A operating voltage? There is a conductor A, conductor B, conductor C. Okay. What is a conductor A operating voltage? With respect to what terminal you measure it? I'm asking you, what is a conductor A operating voltage? With respect to what terminal you have to measure them? Is it with respect to B or with respect to ground? Don't give the answer, just listen to me. Just listen to me, just listen to me. With respect to B, if you measure, it will be line to line, right? Malavika, Aishwarya, Sai Charan. If you measure with respect to B, it will become line to line. It won't become conductor voltage, right? So if you want to know what is conductor A voltage, you should measure that voltage with respect to ground, not with respect to other conductor beside that. Following. So we have to say conductor A voltage with respect to ground B, not with respect to conductor B. Can you please tell me what is that conductor A to ground voltage in your expectation? What is that conductor to ground voltage in your expectation? How much? Is it 220 kV or 220 by root 3? Is it 220 or 220 by root 3? Definitely, it will come to be 220 kV by root 3. It won't become 220 kV. Kindly listen, kindly listen. Conductor A to conductor B voltage, that is 220. Conductor A to conductor B voltage is 220. Conductor A to ground, if you measure, it won't become 220. It will become 220 kV by root 3. Following. What is conductor B to ground voltage? Conductor B to ground also 220 kV by root 3. And what is conductor C to ground voltage? That is also 220 kV by root 3. 220 kV by root 3. All of you understanding this? How? That's what I am saying. Amit Vikram. That's what I am saying here. Kindly observe. 220 kV is conductor to conductor voltage. Means line to line voltage. Line to line voltage. What is that line to ground voltage? So called per phase voltage. Nothing but line to line voltage by root 3. Line to line voltage by root 3. Getting me? Anju Singh is okay. Somashekar Reddy having a doubt. Phase voltage also 220 kV, not understood. Okay, listen here, listen. Somebody is clear. But in delta connection, both line to line and phase voltage are same. Sivanath Ganesh, he said one statement. Listen, I am reading that statement. All of you listen here. Sir, but in delta connection, both line to line and phase voltage are same. Then how it is divided by root 3? You yourself said the statement here. For delta connection, line to line voltage, winding voltages are equal. Not for transmission line, right? For the delta winding, I will say the phase winding voltage, line to line voltages are equal. Not for the transmission line wires. Transmission line, 220 kV is nothing but conductor to conductor voltage only. Right? If you want to know only one conductor voltage, that voltage you have to measure with respect to ground. What is a conductor to ground voltage? 220 kV by root 3. Getting all of you? That will be in fault condition. Is it correct? Yeah, you don't ask me that doubt right now, Gautami. Sir, if ABC terminals are connected in delta winding of transformer, I am talking about, see, I am not disturbing your delta winding statement. Be clear. I am not disturbing your delta winding statement. As far as delta winding is concerned, line to line voltage, phase winding voltage equal. But if you consider with respect to line, per phase voltage of transmission line will be line to line voltage by √3. Okay. So always per phase voltage of line, transmission line is equals to line to line voltage by √3. It's a conductor operating voltage. We are saying it's a conductor operating voltage. Yeah. Okay. If anybody having a doubt, I will discuss later. Okay. Yeah. Means my interest is to tell you, just if I show some line outside, transmission line, three-phase transmission line outside, in what connection the transmission lines are connected? Can anybody tell me? Is it in star or delta? If I say simply three lines outside, transmission lines outside, what connection these are? Star or delta? We can't say. Just I have three conductors, that's it. With a relation conductor to conductor voltage, if you have some number, each conductor to ground voltage will be that line to line voltage by √3. Following all of you, then you don't get a doubt about multiplication of T to the Z base and all. I think all of you clear? Yeah. So let's continue with this. Almost all reactances we got. Now we are going to construct the per phase model of this one. Per phase model. Let's replace each apparatus with its electrical equivalent circuit. Okay, I will continue with this problem after break. After break, I will continue with this problem. Have a break for 10 minutes. We'll meet at 7:30. We'll draw per phase diagram of this and we'll conclude this chapter. Okay. Why I'm writing this? Somebody is saying, whenever I give break, somebody is saying that, sir, audio is not coming, video is not coming. That's why I'm writing this. So I have resumed audio video on screen. Audio video on screen. Okay. So I am continuing with the previous problem, what we are discussing. Previous problem means we want to take the per phase equivalent circuit, right? So let's move to the previous. Okay, this is a question. We have calculated the per unit reactance of all equipment. Now I am drawing the per phase equivalent circuit here itself. Per phase equivalent circuit here itself. Okay. Per phase equivalent circuit in per unit form. Per phase equivalent circuit in the per unit form. Okay, so just look here. Just look here. We have generator. So generator means it will be represented as a reactance in series with the voltage source. So I will show first a generator like this. Voltage source in series with the reactance. Bus 1. Fine. So we have some source here. A generator impedance is how much? Generator impedance J0.99917. J0.9917 per unit. Okay. Bus 1 to bus 2, what we have? Transformer. Bus 1 to bus 2. We have transformer T1. In fact, it is transformer T1. And this impedance, let's call ZT1. How much is that number? J0.1. Bus 2 to bus 3, we have a line. That line we call ZL. Bus 2 to bus 3, we have a line. So this is a ZL line. How much is that line impedance value? J0.2755. J0.2755. Bus 3 to bus 4, again we have a transformer which have an impedance of J0.5. Bus 3 to bus 4, we have transformer T2. This impedance is J0.5 per unit. At bus 4, what you have? Bus number 4, what you have? Yeah, if you want, so let me show. I have not shown the bus numbers earlier. Let me identify them. Bus 1, bus 2, bus 3, it's a bus 4. At bus 4, what you have? Infinite bus. Infinite bus. How you represent that infinite bus in the electrical equivalent circuit? Harshvardhan, why you are asking me again the same doubt? Sir, if transformer delta delta, then Z base of line is 3 times of it, right? What is the question? I said already, your calculation of Z base to the transformer winding may change, but as far as your transmission line is concerned, always line to line voltage equals to √3 times of the per phase voltage. As far as line is concerned, if you are doing the calculations of line, you no need to bother about the transformer winding connections at all, because always for transmission line to line voltage equals to √3 times of the per phase voltage. Okay, right. Yeah, you see this one. See this. Sir, for transformer new voltage base is 12 kV. Already we have shown 11 kV. How come it will come 12 kV? How come it will come 12 kV? I am showing here 11 kV. Listen here, listen. Infinite bus. How you represent that infinite bus in the per phase equivalent circuit? Actually, first we should study what's the definition of that infinite bus here. Before moving to the equivalent circuit of that infinite bus, I should study what are the properties of the infinite bus here. Infinite bus properties. Infinite bus properties. Okay, just look here. See, it's a bus bar. It's a bus bar which can absorb any amount of real and reactive power you inject. Or this bus is having a capability to deliver any amount of real and reactive power you want. That's the property of the infinite bus. Okay, so this bus have a capability of absorbing any amount of P and Q, real and reactive force, as well as delivering any value of P and Q, any amount of P and Q, any amount of real and reactive force, any amount of real and reactive powers. Okay, yeah, listen please. This is one property of infinite bus. Other property I will say, other property. See, actually this infinite bus is a bus at which magnitude of the voltage and frequency remains constant, irrespective of disturbance whatever you create in the system. Irrespective of the disturbance whatever you create in the system, magnitude of the voltage and frequency will be remains constant, right? At this bus, mod V and frequencies are constant, irrespective of disturbances. Irrespective of disturbances. Irrespective of the disturbances, magnitude of the voltage and associating frequencies will be constant. So can we treat this as a voltage source now? Can we treat this infinite bus as a voltage source? Please tell me. Please kindly tell me. Can we treat this as a voltage source? Yes, it can be treated as voltage source. Not only that, it might have a zero internal impedance. Means it's the ideal AC voltage source with zero internal impedance. Okay, yeah. So it can be treated as ideal AC voltage source. Ideal AC voltage source with the zero internal impedance. Zero internal impedance. It can be treated as ideal AC voltage source with zero internal impedance. Okay, and can we say it's a synchronous machine? See, if it is a AC voltage source for you, obviously it's a synchronous machine. It's a AC voltage source, it's a synchronous machine. Okay, synchronous machine. Not only that, the frequency of that voltage developed is constant. Means I can say it's a synchronous machine for which the rotor will rotate at constant speed, irrespective of the disturbances, maybe fault or any other disturbance we have in the system. Fine, right. So in the next property of the infinite bus I am writing. Next property of the infinite bus I am writing. It can be treated as synchronous machine. Synchronous machine with the rotor rotating at synchronous speed. Rotor rotating at synchronous speed. With the rotor rotating at synchronous speed. Not only that, if any rotor rotates at synchronous speed, irrespective of disturbances, whatever you get in the system, maybe power flow variations or any other changes you have, but still it is rotating at synchronous speed, means I use it to treat that machine is having infinite inertia. That machine is having infinite inertia. I will explain about this term clearly while we move into stability analysis. Okay, for time being, it can be treated as synchronous machine with the infinite inertia. It can be treated as a synchronous machine with infinite inertia. Infinite inertia. Okay, these are the properties of infinite bus. So simple way of representing that infinite bus as a ideal AC voltage source with zero internal impedance. Ideal AC voltage source with zero internal impedance. This is the representation of infinite bus. Infinite bus. Yeah, okay. Next, one more thing I want to tell with respect to infinite bus only. Very simple word, very simple word. For example, if you have any short circuit fault at the location of infinite bus, if you have any short circuit fault at the location of infinite bus, something like this, how much amount of current it will circulate? How much amount of current it's going to supply? For example, you assume this voltage is something like E, and how much is this impedance? 0, E by 0. How much current it will supply? Infinite. So infinite bus, in the sense, the fault level at that bus will be equals to infinite. Or else you can say, fault current for the fault at that infinite bus is equals to infinite. Okay, fault level or fault current, both will be used as synonyms. Means both terms we will use alternatively sometimes. Okay, yeah. Anyway, I will remove that fault element and all. So I have to write in the properties actually. I have to write in the properties. At this bus, fault level is equals to infinite, or you can say fault current equals to infinite. Fault current equals to infinite. Okay. So in a simple word, what I can say is, good, Abhijit. It's not a voltage regulator. Sir, is infinite bus is same as grid? You can treat Mohammed if you want. We can treat. Grid is nothing but a voltage source for you. But infinite bus and grid, some difference we have. Grid is a practical term. But infinite bus is a theoretical term. Okay, because I can't expect that internal impedance will be equals to 0. I can't expect that internal impedance equals to 0. Okay, infinite bus is a theoretical one. Yeah, Urokonda Satish, that's what I am saying. Infinite bus internal impedance is 0. And I am treating that as a synchronous machine with 0 internal impedance. But practical synchronous machine will have its internal impedance. Yes or no? But as Mohammed said, you treat this as a grid with 0 internal impedance or 0 Thevenin impedance. Okay, fine. Next, I am doing some sort of extension for this question. Just I will repeat that question what we have here. Just observe. Same question. I am repeating now. Same question I am repeating. Already we have done the problem, right? Okay. See this one. Find Thevenin impedance. With respect to generator terminals. Find Thevenin impedance with respect to generator terminals. That's it. Okay, I will remove this also. Find Thevenin impedance with respect to the generator terminals. Yeah, please kindly look at this question. Yeah, please kindly look at this question. See, if this is a question given to you, they have not mentioned anything regarding the base values. They have not mentioned anything regarding the base values. Base values you can select on your own, any numbers. Base values you can select on your own as any number. Okay, but as it didn't mention the base values, we have to give the Thevenin impedance value in terms of ohms. We have to give the Thevenin impedance with respect to ohms. Okay, fine. But already we have done similar problem earlier. So to reduce the calculation time and all, just I will assume, and now I am assuming base values on the transmission line as 66 kV, 100 MVA. Based on that, we allot the base values for each and every location as it is as of previous problem. Okay, then we have the per phase equivalent model already direct. Okay, but you have to remember that the per phase impedance model is on the basis what you selected in the previous problem. Okay, yeah, if you want, I will write the solution statement here. Solution. Assume or let us choose base values as 66 kV, 100 MVA on transmission line location. Okay, so now I will copy that base diagram. This one, base diagram I am copying like this. So let me show this one. Base diagram I have copied to this place. Observe here. Yeah, done. Base values and all we have, and we constructed the per phase model. You don't need to repeat the solution. I will provide this as a PDF file for you. Just look at the answer what I am saying. Look at the answer. Per phase impedance diagram also constructed on the basis what you selected. I will copy that also. Per phase impedance diagram, this one. Copying this also. The per unit form on the base value selected. On the base value selected, we have given the per phase per unit impedance diagram, something like this. Okay, now with respect to what terminals he is asking us to find Thevenin impedance? With respect to which location? Generator terminals, na? Generator terminal is nothing but bus 1. Generator terminal is nothing but bus 1. So this is a bus 1. So with respect to bus 1, we have to find out the Thevenin impedance. With respect to bus 1, you have to find out the Thevenin impedance. Yeah. All of you getting this one? All of you getting this one? How to calculate Thevenin impedance? First, we should kill the sources. By killing the sources, we have to find out the Thevenin impedance by the view of network analysis techniques. Okay, I'll kill this source. I'll kill this source also. Killing the source means a voltage source means you should make a short. Current source means you have to make it open. We have to make that value 0. Make that value 0. Voltage value 0 means shorted. Here also 0 means it is shorted. Let me copy this diagram. Right. So by killing the sources, I will write in the next slide. By killing the sources, so this source I am removing. This also I am removing. Now I can keep a short here, and here also it's a short. Now you can see left side you get the J0.9917, right side 0.2 and 0.4755. Okay, so let me redraw this. J0.9917 on one side, other side J0.4755. It is bus 1. So with respect to bus 1, we have to calculate Z Thevenin. So I can say with respect to bus 1, ZTH, parallel combination J0.9917 in parallel with J0.4755. 4755. Okay, calculate this number. J you can take common out. Right, 4755 by summation 9917 plus J0.4755. Yeah, please calculate this number. 0.9917, 0.4755 So this value will be 0.3213. J 0.3213. It will be in per unit domain. It will be in the form of per unit. Per unit. How much is this value in ohms? How much will be this value in ohms? Means we have to multiply this Z Thevenin with Z base, with the value of Z base. Okay. So Z Thevenin in terms of ohms is equals to Z Thevenin per unit multiplied with Z base. A Z base at which location we have to consider? Z base at which location? At which location you calculated Z Thevenin? With respect to that location only, we should take up the Z base. Bus 1, right? Bus 1. At the bus 1 location, what are the base values? What are the base values at the bus 1 location? 11 kV, 100 MVA. 11 kV, 100 MVA. With these base values, we have to calculate the Z base. Anybody having a doubt? Tell me now. Please ask. Anybody having a doubt? Very simple. At what location you want to find Z Thevenin? At that location only we should calculate the Z base. Logical way of thinking. That's it. Okay. So at bus 1, I'll write here. At bus 1, Z base per phase. You write V base per phase square by S base per phase. What's the V base per phase? 11 kV by root 3. Square. What is the S base per phase? S base per phase is 100 mega by 3. Okay. So 3 will be cancelled out. 11 square by 100 you get 1.21 ohms. You get 1.21 ohms. So that 1.21 multiplied to this J 0.3213. So Z Thevenin with respect to bus 1 in ohms will be J 0.3213 into 1.1. Okay. So you please calculate this number how much? 0.3213 into 1.21. So this value will be J 0.389 approximately J 0.389 ohms. Sir, in problem did they give? Definitely. Just like that, they can't ask you to find Z Thevenin, right? They should tell with respect to what location you have to find. Okay? Sir, suppose if they want to find Thevenin impedance, that will be 0. Harshvardhan, simple answer. 0. Sir, delta, where you are calculating what we call Thevenin impedance. Is it at terminals or on the winding? Uravakonda Satish, where you are calculating the Z Thevenin value. Is it on the winding or on the terminals? Terminals. If you are talking about terminals, no need to bother about the delta star and all. Yes or no? Yeah. Calculating on the terminals, not on the winding. See, if you are calculating, listen please. If you are calculating winding impedance, delta winding impedance, then only we should be a bit careful. Else, if you are calculating Thevenin impedance with respect to some terminal, you no need to bother about that formula what we have discussed for delta. Simply you can go for V base line to line square by S base 3 base as a Z base practice. Following? Okay. Next question I am asking you with respect to bus 2, what is the Thevenin impedance? You do that calculation as a homework. Homework I am saying you. Find Z Thevenin in ohms, ZTH in ohms with respect to bus 2 are better because bus 2 is not there. With respect to HV terminals of T1 transformer. HV terminals of T1 transformer. Okay. You do that calculation later. But after calculating Z Thevenin per unit from the circuit, bus 2. With respect to bus 2 means left side you get J1.0917. Right side you get J0.3755. Connect in parallel. You will get some number in per unit. What is jet base? Bus 2 location base values you have to consider. What are the base values at the bus 2? Bus 2 location base values. What are the base values at bus 2? 66 kV, 100 MVA. With respect to these base values, we have to calculate the jet base and we have to multiply to the per unit number. All of you getting this? Tell me please. Line base value, how chosen, sir, initially? Yeah, actually, dear Vishnu Ajit, he has already have done the previous problem, already have some solution there. That's why I selected the same base values as a previous problem. For example, if it's a new problem asked for you as a fresh one, you choose your own base values at any location. That's your wish. Okay. With respect to those base values, you calculate jet Thevenin per unit value, and you convert that into absolute value with respect to the base impedance what you have selected. Following, Vishnu? Yeah, good. So let's move to one more question. This is a homework to you. Jet base is different number. Please be clear about the jet base number while you are converting per unit to absolute. Yeah, let's take last problem in this per unit impedance diagram construction. So I want to explain something to you by this problem actually. I want to explain something to you by this problem. Kindly go through this question. Go through this. A three-phase synchronous generator rated for 13.2 kV, 150 MVA with XD 0.6 per unit. Means reactance of generator is 0.6 per unit. Obviously, you should get this thing into mind. This 0.6 per unit is on the base values of 13.2 kV, 150 MVA per phase reactance. Okay, to a transformer. This is a transformer connected. The three-phase transformer is constructed by using 3 single-phase transformers. Okay, 3 single-phase transformers we have. Means first single-phase transformer, primary, secondary. Second single-phase transformer, primary, secondary. Third one, primary, secondary. These 3 transformers, windings, primary windings, we should connect to get a delta. 3 transformers, secondary windings, we should connect to get a star. Okay, next. Each single phase transformer is rated for 13.2 kV by 127 kV, 50 MVA, X equals to 0.2 per unit. Means he said the ratings of only one single phase transformer. These ratings, what they have given, we should convert into the 3-phase transformer block. That's the first thing we have to do. After this, what they said is the Thevenin reactance with respect to HV side of the transformer is dash ohms. What is the Thevenin reactance of the transformer with respect to HV side? Okay. So I will move to the next slide to do the solution. He didn't mention the base values. That's your wish, what you select. Okay. First, let's be clear about this transformer. After that, we will look into the complete problem. Let's discuss little about the transformer first. Solution. 3-phase transformer constructed by using 3 single-phase transformers. 3 single-phase transformers. I will show 3 windings now. 3 windings. Primary 3 windings. Secondary 3 windings. Observe carefully. What is that connection? Delta star, na? Delta star. In that way, I will draw. This is primary of the first transformer, P1, primary of the first transformer. See, secondary, how I am drawing, secondary. Secondary of the first transformer, P1, S1, parallel that you have to observe. It's not exact physical diagram, schematic diagram, parallel. Okay. P2, transformer, second transformer, primary, S2. Second transformer, secondary. Okay. Next, third transformer, primary. Third transformer, primary. Third transformer, secondary. Third transformer, secondary. Yes. Done. Next. Listen, please. Listen. 3 primary windings, P1, P2, P3 will be in delta. I will join them in delta. Join them in delta. I'll take 3 lines out. Like this, I can say conductors coming out. 3 wires coming out. Secondary 3 windings will be connected in star. According to this picture, I am following. According to the single line diagram given, I am following. Okay. Secondary 3 windings are in star. Like this, we have joined. And I will take 3 outcoming terminals now. Like this, we are showing 3 outcoming terminals. Done. Over. Next, what will be the voltage rating of each single phase transformer? Is said primary 13.2, secondary 127. Winding ratings. Primary P1 rating is 13.2 kV. S1 rating is 127 kV. S1 rating is 127 kV. Can anybody tell me what is line to line rated voltage on the primary side? What is the line to line rated voltage on the primary side? Yes, Charan Reddy. Yeah, please tell me what is that line to line voltage on the primary side? Why delta star, sir? They have given in the problem. 13.2. That's it. Bhumika, 13.2 kV only. Because in case of delta, winding voltage, line to line voltage, both are equal. Yes or no? 13.2 kV only. Getting me? Okay. Again, I am asking a silly question to you. Try to answer me. If I ask, what is this terminal voltage? Means this point voltage. Anybody, what is this voltage? What is this terminal voltage? Means what is this node voltage? I've shown there. 13.2 or 13.2 by root 3? It will be 13.2 by root 3. Good, very good. That's what I said. Terminals you take, terminals of delta you take, each terminal voltage is 13.2 by root 3. Line to line voltage, 13.2. Winding voltage, 13.2. That clarity you should have. That clarity you should have while you are doing the problems. Okay. So if you want, I'll write this one, VA 13.2 by root 3 kilowatts. Just for your clarity. I don't use this one anywhere. Okay. Next one. What is line to line voltage here? In case of star winding, what is this line to line voltage? Anybody please tell me? What is this line to line voltage? 127 into root 3 kilowatts. 127 into root 3 kilowatts. How much is that number? How much is this number? 220 kV. 220 kV. Next, one more thing. Listen, one more thing. What will be the line to line voltage ratio of this transformer? Primary line to line voltage rating 13.2 kV. Secondary line to line voltage rating is 220 kV. That's fine. What will be the power rating? You know, each winding having a rated power of 50 MVA. Each winding has a rated power of 50 MVA. Then three phase in the sense, it will be 3 into 50, 150 MVA is a power rating of this three phase bank. Three phase transformer bank. Okay. Yeah. So let's write in the next slide. So three phase transformer ratings are 13.2 kV by 220 kV, comma 3 into 50 MVA, 150 MVA is that number. So 13.2 kV, it's a line to line primary and it's a line to line secondary. Okay, next one. What is the reactance value in the per unit form? What is the reactance value in the per? He said it is 0.2 per unit, right? He said it is 0.2 per unit. 0.2 per unit for each winding. Listen to me. All of you listen to me. 0.2 per unit is a winding impedance. On which side? Is it on primary side or secondary side? Tell me please. Is it on which side? Primary side or secondary side? Which side you want me to consider? Both. Any side. Okay, good. Let's write. You don't need to draw this diagram again. I'm taking this one for explanation purpose. In the next slide, you no need to draw this. Let's take here itself. Listen. See, for example, if you consider that 0.2 per unit on the star side, 0.2 per unit on the star side. So this reactance is 0.2, this reactance is 0.2, this reactance is 0.2. As a total reactance referred to the secondary side only, obviously these reactances will turn to 0. Reactances will turn down to 0 on the primary side because total reactance we have taken onto the secondary side only, 0.2. So this 0.2 per unit reactance simply act as series impedance in this manner. Simply, it will act as series impedance in this manner. 0.2. Okay, I have taken those impedances out. All of you getting me? Yeah, I don't know whether you are following this or not. All of you getting this? 0.2 per unit is each winding impedance that is connected in series with the line. So I have taken that impedance out into the line. 0.2 per unit in the equivalent circuit. Then, can you tell me please, what is this per phase impedance now? What is this per phase impedance of transformer? 0.2 per unit. Per phase impedance of transformer will be 0.2 per unit. Yes or no? Yes. Why 0 on the primary? Because total impedance we have taken on secondary. So Z per phase of this transformer is nothing but J0.2 per unit. Z per phase of this transformer is nothing but 0.2 per unit. Clear? Now you have a doubt. That, sir, why you are taking that impedance of transformer on the star side? Why can't we take on the delta side? Why we are taking 0.2 taken out to draw per phase network? Neelamati, to draw the per phase network. Okay. So 0.2 impedance can be considered on any side. That's correct. So now I am saying you 0.2, why you are taking on star side? You take on delta side, you keep zeros on the star side. You take on delta side and you keep zeros on this side. That can also be done, right? Yes or no? Yeah. Nobody is responding. Okay. So I will show that in the next diagram. Okay. Here. This is our transformer. Now it's a second way of writing that. Now I will keep these secondary winding leakage impedances 0. Primary winding leakage impedances or reactances will be 0.2. primary winding leakage reactances will be 0.2 because total reactance we have taken onto the delta side. Yeah, obviously it's the effective value. Sai Charan Reddy, even though they didn't said, we have to take that as effective value only. Yeah, kindly listen. So if it is delta, you want to do per phase analysis. Definitely this delta you will convert to star, right? After converting this delta connected 0.2 impedance into star, you get the per phase impedance of the star. You get the per phase impedance of the star. All of you getting? Yeah. Now, can you convert this delta to star? By converting the delta to star, what will be that each reactance value in the star? What will be the leakage reactance in the star? 0.2. I think you got the thing why I have explained yesterday about the delta to star conversion. Okay. All of you clear? Even you convert this delta to star will give, after converting delta to star, Z per phase will be remain same as J0.2 per unit only. Because in per unit, delta to star conversion, particularly three-phase delta converted to star, you don't have any change in the per unit impedance. Again, Kushal is saying by 3. Okay. So now I think I can proceed with the calculations and all now. I'll take in the single line diagram in the next slide. Directly, I will write the ratings and all. We deal with a single line diagram from this point. Let's move to the next slide. So I'll show this was a single line diagram given. We have a generator connected to one transformer here, and then here it's an open circuit. Ratings, pick up generator ratings 13.2 kV, 150 MVA. And what's the generator reactance given? Xg. Generator reactance how much? 0.6 per unit. On what base? 13.2 kV, 150 MVA base. Transformer ratings. 3-phase. Just now you found 13.2 kV by 220 kV. Power rating of this transformer is 150 MVA. Transformer reactance. Just now you calculated 0.2 per unit. Transformer reactance is 0.2 per unit. Let's look back to the question, what they asked. The Thevenin reactance with respect to HV side of transformer. HV side of transformer means with respect to this side, we have to give the Thevenin equivalent reactance in what units? Not in per unit, ohms. Should give the number in ohms. Okay. So if you want to give that number in ohms, already the values are given in per unit. May not be on the common base. May not be on the common base. Now we should select the common base. We should find out the reactances in the per unit on the common base. We should draw that model and find out the Thevenin base. Okay. Yeah. So let's write. Let's write here. Let us choose base values. That's your wish now. Because in the problem they have not mentioned. You can choose any base value. Let us choose generator ratings itself as base values. Let generator ratings chosen as base value. Base values. So I can say 13.2 kV 150 MVA at the generator location, and it's valid up to the transformer primary. Valid up to the transformer primary. From secondary of transformer, base value, base MVA 150, no change. But voltage base will vary according to transformation ratio. 13.2 primary base, transformation ratio 220 by 13.2. It will come to with 220 kV. Means observation is now old and new bases are equal. Old and new bases are equal for both apparatus. So we don't have any change in the per unit reactance values. Okay, you write that statement. No change in per unit, sorry, old and new base values. No change in old and new base values for both apparatus. Both apparatus. Okay, let's draw that per phase diagram now, because per unit impedances will be remain same. So per phase equivalent circuit, per phase network. First generator, represented like this. Generator. And what's the generator impedance? J0.6. Generator impedance is J0.6 per unit. We have some voltage source here. Next, after generator, what you have? Transformer. Transformer impedance is J0. Transformer impedance is J0 per unit. So after transformer, what we have? Open circuit. After transformer, you have a open circuit. Now, with respect to HV side of transformer means, as I said, with respect to this side, you have to find and you kill the source. By killing the source, the series connection of these two is a Z-Thevenin value with respect to HV side of transformer. With respect to HV side of transformer, ZTH is nothing but generator impedance plus transformer impedance. It will be J0.8. That's in per unit. That value was in per unit. We have to convert this into ohms. Yeah, I'm showing last slide. If somebody is writing, please complete it quickly. Yeah, Alan Matthew, that's correct. 0.2 per unit is on 127 kV base per phase. 127 kV per phase. 50 MVA per phase. Okay. If it's converted to line, it will be 220 kV. 220 kV, 150 MVA, right? Alan Matthew. 0.2 per unit is on 127 kV per phase base. Obviously, 220 kV line to line base. So the per unit will change. How it will change? What's the old and new base? What's the old and new base? Both are same, right? Old and new base, both are same. Just please be clear. Old base 220 kV, new base 220 kV. Do you want to take per phase? You take 127 kV per phase, old base. 127 kV per phase, new base. If you are taking old base as per phase value, new base should be also per phase. If you are taking old base as line to line, new base also should be taken as line to line. Why we are adding, sir? Both they will be opened. How it will be opened? Yes, follow network analysis, Mr. Anonymous attendee. Go through network analysis. These two are connected in series. Circuit was closed here. Yeah. See, you have to multiply this per unit impedance with Z base. What is Z base? On which side? HV side. HV side, what are the new base values? 220 kV, 150 MVA. With respect to these two, you calculate Z base per phase, multiply to the per unit number. Okay. So on HV side of transformer, Z base per phase value. You want to take per phase numbers? You take per phase, no issue. V base per phase is 220 k by root 3 whole square. S base per phase is 150 mega by 3. Root 3 square, 3 will be cancelled. Kilo square, mega will be cancelled. 220 square numerator, 150 in the denominator. You calculate this value. How much? 220 square by 150. This number is 322.67 ohms. 322.67. So you can write that Thevenin impedance in ohm, J0.8 per unit number, base number is 322.7. So you do this calculation, you get 258.13. J 258.13 ohms. And we have to give only reactance in the answer. Only reactance in the answer. So answer will be imaginary part of this, means 258.13 ohms. Only reactance in the answer. So this is the end of this chapter. That is per unit quantities are representing the power system network in the per unit domain. So now we will be starting the symmetrical components. Next chapter, symmetrical components we are going to start. Symmetrical components. Okay, so I'm closing this file. If anybody have doubt, you can ask me. Yeah, definitely today itself, may not be today, tomorrow morning you will get. Tomorrow morning you will get the notes. Type of winding while calculating. See, if you are calculating transformer impedance, it may be required to check whether the transformer winding is in star or delta. Okay. Else, I said you already, if it's a delta winding impedance, then only we should be careful. Else, otherwise, always you can take the formula simply V base line to line square by S base 3 base as a Z base. So if it's asked to calculate on bus 1, then only generator impedance will be considered. Correct. Sajjan Singh, if they have asked to find jet Thevenin with respect to generator terminals, it will be open, no? This side, if you want to find with respect to this terminal, this side will be open. It won't carry any current. The current will flow only in 0.6 per unit. So 0.6 per unit is your answer in the per unit form. We have to convert that into absolute form. We have to multiply with the Z base per phase at the generator. Z base per phase at the generator. What is the Z base per phase at the generator? 13.2 K square by per 50 mega. Okay, base impedance will change. Okay, so I'm closing this file and I will be going to the next chapter. So it's a chapter 2, symmetrical components. Okay. Yeah. See, before introducing this symmetrical components and all, so first I am taking 3-phase networks here. 3-phase networks. Case 1, I will say. Case number 1. So I'm drawing one 3-phase network. Kindly go through it. Voltage source. 3-phase voltage source. 3 voltage sources we have here. So I am showing 3 lines. Like this, I am showing 3 wires here. 3 impedances also, you can say something like this. At the end, I connect 3 resistors like this, doing the connection. Okay. Okay. Next, I am saying some numbers here. Yeah, look here. I will copy this diagram because I have to draw the same diagram for case 2 also. Case 2 also I have to draw the same diagram, but I will show the changes. I will show the changes in here. Okay, look here. Case 1, this source EA 100 at an angle 0 degree volts. This source EB, phase B source, 100 at an angle minus 120 degree volts. And this source is EC, 100 at an angle plus 120 degree volts. Okay, and these reactances I am saying, of course, impedance J2 ohms, J2 ohms, J2 ohms. And these resistance values I am saying, resistance values 10 ohms of each, 10 ohms. Okay, fine. Listen. Find out current in the phase A line, current in the phase B line, current in the phase C line. What are the currents? IA, IB, IC. What are the currents? IA, IB, IC. Anybody? Yeah, actually, Yugashri, the way how we are discussing itself is required for GATE as well as IES. Okay, so it's not lengthy process what we are discussing. As we are learning, you feel that it's a lengthy process. Okay, so always solving a problem with a shortcut is not at all possible. Shortcut in power system means it will be eliminating the options given. That's it. Other than that, you don't find any shortcut. Yeah. Listen, what's the IA current here? How this system looks to be for you? How this system looks to be? Balanced. Why means if you look at the voltages, 100, 100, 100, magnitudes are equal. The angle difference between any two voltages, 0, minus 120 means 120 degree shift. Minus 120 to 120, again 120 degree shift. 120 to 0, 120 degree shift. So voltage source is balanced. Voltage source is balanced. All these phase impedance are equal. All these three phase impedance also equal. Means as a whole, I can say our system is a balanced one. We can do per phase analysis on this. Okay, so I can write here, it's a balanced system. It's a balanced system. Balanced system. See, as it is a balanced system, simply what I can write IA is EA by J2 plus 10, because J2 and 10 are connecting series. What's the IB current? EB by J2 plus 10. What's the IC current? EC by J2 plus 10. Like that, we can get IA, IB, IC separately. How many equations you are writing? 3 equations to find out 3 phases currents. IA, IB, IC currents. Okay. So I will write these currents quickly. IA current, EA by J2 plus 10. EA by J2 plus 10. Yeah. So calculate this number how much? 100 by 10 plus 2i. 10 plus 2i. Magnitude will come 9.806. 9.806. Angle will be minus 11.31 degree amperes. That's the IA current. What's the IB current? IB. EB 100 at an angle minus 120 degree by J2 plus 10. J2 plus 10. So I think magnitude will come same. 9.806 only. angle will be minus 131.31 degrees. And IC current, if you calculate, IC 100 at an angle plus 120 degree voltage by impedance summation J2 plus 10. So this will be again magnitude 9.806 only. The angle will come to be, so 108.66 degree. 108.6. Like this, you get IA, IB, IC currents. Of course, it's a balanced system. Neutral voltages may be 0 here. This neutral voltage will be 0. This neutral voltage may also be expected as 0. And we can do phase analysis. A separate, B separate, C separate. We got these three currents. Getting all of you? Good. Good analysis already. Okay. Let's move to case 2, where I want to show some difference. Case 2. So if you have completed, I will move. I will wait for 5 seconds. Please complete it. Okay. So it's a case 2 now. Case 2. Let's show these numbers. It is J2 ohms, J2, J2. And these resistor values are 10 ohms. Each resistor's value 10 ohms. And see this. This voltage, EA, EA 100 at angle 0 volts. This voltage, EB 110 at an angle minus 100 degree volts. This voltage, EC 105 at an angle 105 degrees volts. Like this way. Phase A phase A source voltage, phase B source voltage, phase C source voltage. 100 at angle 0, 110 at angle minus 100 degree, 105 at angle 105 degree. Again, the question is find out IA current, IB current, IC current. That's the question. The question is again to find out IA, IB, IC currents. Anybody? Tell me please how to calculate IA, IB, IC. How to calculate IA, IB, IC. Yeah, Sunil. How to calculate in virtual calculator? What you are doing now? Are you learning or are you practicing virtual calculator? If you want me to teach the problems only with virtual calculators, we no need to study power system analysis at all. I said already, you are in a learning stage. Please go with the regular calculator, what you use in your BTech. Okay. The problems what you get in the GATE examination are in the view of virtual calculator only. If you want to solve the problems only in the view of virtual calculator, power system analysis we can't study. Yeah. Let's move. What's IA current here? Anybody? IA current. We can't find as easy we have done in the earlier case. Because voltage source is unbalanced here. Even though your impedances are balanced one. Phase A total impedance 10 plus J2. Phase B total impedance 10 plus J2. Phase C total impedance 10 plus J2. But your sources are unbalanced. No, source is unbalanced. So I can say overall system is unbalanced. Overall system is unbalanced. Okay, done. In this case, what you have to do is you apply KVL between phase A and phase B. Apply KVL between phase A and phase B. Phase B and phase C. Phase C and phase A. Total, how many KVLs you have to apply? 3. AB 1 KVL, BC 1 KVL, CA 1 KVL. 3 KVLs. How many equations you have to solve now? How many equations you have to solve? Obviously 3 equations, right? So I can say 3 KVL equations. 3 KVL equations has to be solved. Has to be solved to find IA, IB, IC currents. Find out IA, IB, IC friends. We have to solve 3 KVL equations, right? How many equations you are solving in the previous case? Anybody please tell me? How many equations you are solving in the previous case? Yeah. How many equations you are solving in the previous case? 3. 3 equations only, right? In the previous case also, we are solving 3 equations, IA, IB, IC. Here also you are solving 3 equations. But what is the difference between the 3 equations in case 1 and 3 equations in case 2? What's the difference between the 3 equations in case 1 and 3 equations in case 2? See, in the case 1, we can solve these equations independently. But here, the 3 equations what you need to solve are coupled together. That's the main problem what we face in case of unbalanced system of analysis. Okay, number of equations to be solved remains same, but the 3 equations what we need to solve are coupled, right? So let me write that statement. So in the unbalanced system analysis, three equations to be solved are 3 equations to be solved are coupled equations. Okay, so it is difficult to do the unbalanced system analysis. So it is difficult. Yeah. So in order to simplify this unbalanced system analysis, the 3 coupled equations what you have now, 3 coupled equations are going to be converted into set of uncoupled equations. These 3 coupled equations we are going to convert into set of uncoupled or decoupled equations with the help of the symmetrical components. Okay, right. So by using symmetrical components theory, the set of coupled equations can be converted into uncoupled equations. Set of coupled equations can be converted into uncoupled equations. Okay, so it was proposed by C.L. Fortescue, a symmetrical components theory. So I will be extending our discussion with respect to this symmetrical components theory only from this point. Okay. So if you have done, I will move to next slide to give that definition of the symmetrical components theory. So please complete it quickly. I will wait for 5 seconds. Yeah, okay. So the next heading is symmetrical components theory, or you can say sometimes theorem. Theory or theorem. It was proposed by C.L. Fortescue. According to this symmetrical components theory, a set of, listen please, a set of n phase. I'm saying in the view of n phase system. Later on, we convert the same definition to 3 phase system. Okay, let me write better. A set of n phase unbalanced phasors will be or can be converted into n minus 1 sets. N minus 1 sets of n phase balanced phasors balanced phasors. N minus 1 sets of n phase balanced phasors of different phase sequence. Different phase sequence and one set of n phase, one set of n phase cophasal phases. Cophasal phases. One set of cophasal phases. This is a definition. So this is the definition of the symmetrical components theory. This n phase definition, what that professor has given, we are converting into a three phase. Means what you should write is a set of three phase unbalanced phasors can be converted into n minus 1 means 2. Two sets of three phase balanced phasors of different phase sequence, right? And one set of three phase cophasal phasors. Okay, right. So, but rather than writing the statement, simply what I will say is, for three phase system, one set of three phase unbalanced phasors, will be converted to what you can write here. Two sets of three phase balanced phasors of different phase sequence. Balanced phasors of different phase sequence. Okay, and one set of three phase cophasal phases. Cophasal means in phase. Cophasal means in phase. Cophasal phasors, or you can say in phase phasors. Okay. So before discussing about this unbalanced phasors to be converted into set of balanced and cophasal phasors, first we have to learn on what quantities in the power system analysis can be, on what quantities we can apply the symmetrical components theory. On what components we can apply the symmetrical components theory. Like in the power system analysis or even in network analysis, you can find different terms like voltage, current, real power, reactive power, complex power, impedance, flux. Voltage means you can say electric flux, or you can say magnetic flux. These are various terms you can find, voltage drops. Okay, among these terms, on what quantities or on what components we can apply the symmetrical components theory. Okay, yeah, that we have to learn. Okay, so I can say symmetrical components can be applied on so I'm writing all those terms here: voltages, currents, powers, maybe real power, reactive power, complex power, and then impedances, fluxes, magnetic flux and electric flux, electric and magnetic, and you can say voltage drops. These are various terms. Now, the statement is not to say on all these things we are capable to apply the symmetrical component. That's not the thing. From these things, what I have given, select on which components we can apply the symmetrical components theory. On which terms you can apply the symmetrical components theory. Voltage can we apply? Voltages. Yes or no? Can we apply on voltages? symmetrical components can we apply on voltages? Yes. Currents can we apply? Yes. Powers can we apply? Powers. No. Volt powers we can't apply. Powers we can't apply. Powers we can't apply. Impedances can we apply? Impedances. Can we apply symmetrical components on impedances? No. Impedances we can't apply. See, one basic term what you have to think here is, before applying symmetrical components on any quantity, what you have to check is whether that is a phasor or not. If it is a phasor, then only we can apply symmetrical components on them. Impedances are not phasors. Impedances are not phasors. Those are simply complex numbers. Impedance are simply complex numbers. Powers are not phasors. Those are again simply complex numbers. Do have a phase shift of 120 degrees from one phase impedance to other phase impedance? No. Do have a shift of 120 degrees from one phase power to other phase power? No. Then obviously powers and impedance are not phasors, not phasors. So we can't apply symmetrical components on it. But sometimes you might be studying that positive sequence impedance, negative sequence impedance, or zero sequence impedance. But those impedances, positive, negative, and zero sequence impedances, are not calculated with the help of the symmetrical components theory. Positive sequence impedance means impedance offered by the apparatus for positive sequence current. Okay, negative sequence impedance means impedance offered by the apparatus for negative sequence current flow. So those sequence impedances are not calculated with the help of the symmetrical components theory. Tell me now, fluxes, whether these are phasors or scalars. Fluxes, whether these are phasors or not. Yes, obviously these are phasors. Yeah. Why? Electric flux depends upon voltage variation. Magnetic flux depends upon current variation. So obviously fluxes are phasors only. We can apply symmetrical components on the fluxes also. Voltage drop, phasor. Current into impedance. Current is a phasor, right? So obviously voltage drop is also a phasor. Okay. Somebody's asking me, but powers are represented in the phasors, sir. Vishnu Ajit, please kindly listen. Can you show the power in the phasor diagram? Can you show the power in the phasor diagram? You might have studied phasor diagram of transformer, generator sometime. Have you shown power in the phasor diagram anyway? Tell me. No, power is not a phasor. Yeah. So remaining all, we can apply the symmetrical components. So to avoid the doubt, I am removing these powers and impedances. So symmetrical components can be applied on these things because all these terms what we have written are phasors. So you can write symmetrical components can't be applied on symmetrical components can't be applied on impedances and powers, which are not phasors. Okay, so we will stop at this point for this day. Tomorrow, what we'll do is we'll take voltages here. One set of three-phase unbalanced voltage will take. Then we'll take two sets of balanced and one set of co-phasor, and we'll continue with the mathematical study mostly. Okay. Yeah. So if you have any doubts, you can ask me now. So I have lowered all the hands. Please raise your hands now if you have any doubt.
Hello, sir. Good evening.
Good evening. Tell me.
Sir, about this symmetrical component, you said 1.0 positive sequence and negative sequence. Sir, can you repeat that point? I did not understand.
Anyway, we will discuss those terms tomorrow. If you want, you will listen. See,
Yes,
we said
sir.
two sets of three-phase balanced phasors, right?
Yes.
One set is called as positive sequence, other set is called as negative sequence.
Oh, okay, sir.
Okay, tomorrow we'll elaborate it.
Okay. And sir, on the slide number 2,
Okay.
sir, here this star 10 ohm, is that load?
Yeah, that's your wish, what you feel.
So sir,
It may be a load. It may be a load. Okay.
sir, when we consider balance system, then there only J2 should be equal, or J2 plus 10 ohm and J2 plus 10 ohm should be equal.
J2 plus 10 ohm should be equal. Not only line impedances, load impedances also should be equal.
Okay.
Overall
Okay,
phase A impedance, overall phase B impedance, overall phase C impedance. These three must be equal. Your voltage source should be balanced. Then only the voltage source will drive balanced currents.
okay, sir. And sir, that infinite bus problem that we discussed,
Okay.
sir, in that we found 66 kV base value was given for transmission line. And from that we calculated 11 kV. So sir, that 11 kV was for that infinite bus.
Yes.
Okay, sir. Thank you. Okay, thank you, sir.
Pawan Kumar.
Sir, good evening, sir.
Good evening, Pawan
Sir.
Kumar.
Sir, today's first sum, sir. Second sum, sir.
I have to close this actually. Wait it. Okay. Okay, tell me what's the doubt you have in that?
Sir, that new base value you have taken at the T1, no, sir. Secondary of the transformer T1.
Okay. First problem.
Second problem, sir.
Is it in per unit impedance diagram?
Yes, sir. Yes, sir.
What is that problem? Is this problem?
Wait.
Can you tell me voltage is there?
Not this problem, sir. Second problem. Yes, sir. No, not this. Generator 12 kV.
Ah.
Sir,
This
if you
one?
take, yes, sir.
Tell me.
Sir, if we take new base values at the generators, will we get the same answer, sir?
New base values as generators you want?
Yes, sir. We'll get the
But
same.
they have given base values, no problem, right?
Yes, sir. They given base value at appropriate location, but
Okay.
you have taken at the T1 of secondary.
Means transmission line we have taken. Why?
Yes, yes, sir.
Why this
If
one
we-
is line voltage rating is matching with the base value.
That's what I'm asking, sir. If we take at generator side, we will get
Then
the same
definitely you
answer.
get a different answer. Your answer will go wrong.
No, sir. That is our wish, no, sir. We can take anywhere, no, sir. Base value.
Not your wish. He said here appropriate location, right?
Okay, sir.
Appropriate location means you have to match the base voltage what they have given with the rating of the apparatus, voltage rating of the apparatus.
Okay, sir.
Whichever the apparatus is having voltage rating close to that base voltage value, at that apparatus location we should consider that base.
Okay, sir. Okay.
That's the
So
meaning
then-
of appropriate location.
Okay, sir. Sir, once open that next page, sir.
Okay.
Sir, how you are calculating here V base, sir?
Which side?
At generator side.
Okay. See, V base on generator side or V base 1 by V base 2 you take. Bus 1, bus 2 na?
What, sir? What, sir?
Bus 1, bus 2.
Okay, sir.
V base bus 1 by V base bus 2 must be equals to voltage rating 1 by voltage rating 2 of transformers.
Okay, okay.
So V base 1 equals to what? V base 2, 66 into V1 by V2, 11 by 60. It will come to be 11.
Okay. Sir, in
Okay.
previous sum also you did like that only, sir.
Every problem it will be like that only.
Sir, sir, what?
Base voltages ratio must be equals to ratio of the ratings of transformer.
Okay, sir. That means bus values.
Yeah.
Okay, sir, next to that, what is infinite bus, sir? I didn't understand.
Infinite bus is a bus for which we have a big power system network connected.
Okay, sir.
Big power system network means it consists of many number of generators, lines, loads, and so on.
Okay.
But if you look from that bus, that big power system network will act as an ocean.
Okay.
It can take any amount of power you inject. It will supply any amount of power you want. It's like an ocean you feel.
Okay.
Okay, from ocean, if you take a bucket of water, or if you give a bucket of water, is there any change in the ocean?
No, no,
It's a
sir.
kind of thing, actually.
Of course.
Okay.
You have given some points, no, sir. It's
Yeah.
like a synchronous mission.
Technically, if you speak, infinite bus means it's a bus bar for which a large number of generators and loads are connected, and it will act as an ideal AC voltage source.
Okay.
Means, for example, I'll show here. For example, if this is an infinite bus, I'll say. If it's an infinite bus, look here. If you add one generator to this, or if you add one load to this, or if you add some other equipment to this bus voltage is not going to be disturbed.
Okay, sir.
And if you remove something at the infinite bus, but still the bus voltage will be remain same, operating at the fixed frequency.
Because of the generator.
Because of this big system.
Okay.
This generator is a small one, but the system is very large one.
Okay, sir.
You assume this is an Indian power system network.
Okay, sir.
Of 370 gigawatt capacity. Okay, sir. 370 gigawatt capacity Indian power system network. To the power system network, I am adding 50 megawatt generator.
Okay, sir.
Even if we add 50 megawatt generator or remove 50 megawatt generator at that bus bar, do you have any change in the voltage?
No, sir.
May not be. That's the infinite bus.
Okay. Okay, sir.
Okay.
Okay.
Next. Suryan.
Hello, sir.
Tell me, Suryan.
Sir, a line connected to delta, we have taken that line voltage, no, sir, with respect to ground divided by root 3. Sir, how we got that divided by root 3, sir? Sir, my doubt is, we generally derive that divided by root 3 depending upon the phasor diagram only, no, sir. But how we can
the phasor diagram?
Same by drawing the phasor diagram, no, sir.
Yes, correct.
Okay, sir. Sir, another doubt, sir. Sir, in the question that 66 kV we have taken in transmission line, no, sir. If suppose they have not mentioned the word at appropriate location, we can.
But still, you should take on transmission line.
Okay, sir.
There is one gate question. They have not mentioned the statement as appropriate location.
Okay, sir.
But still, they said simply base values are these numbers.
Okay, sir.
Okay, but still you should match that base voltage with the voltage rating of apparatus, and you should take that base value at that location.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Okay, fine. Praneeth. Jubilee Praneeth.
Good evening, sir.
Good evening, Praneeth.
Sir, second sum we discussed now, sir, today, 88 page.
88. Okay.
Yes, sir. Here we had two formulas for Z base per phase, no, sir.
Okay. See, what you are calculating? Are you calculating impedance at the terminal or winding impedance?
On winding, no, sir. Yes.
Winding. Winding means you should check what is the connection of winding.
It's a delta.
With respect to that, you should select the base values.
Okay, sir.
As it is delta, V1 base per phase value, V1 base line to line values are equal.
Yes, sir.
But S1 base per phase is by 3 of S1 base 3 phase.
Okay. Sir, if I use the
Z1 base per
reference,
phase on this kind.
sir, if I use the formula that V1 base line to line square by S1 base 3 phase, no, sir.
Then it will come wrong, right? When we have
Three
to use
times-
it, even see what is the per phase base impedance formula? This one only, right? This is the original formula.
Yes, sir.
For anything, is either it is star, delta, transmission line, anything, V1 base per phase square by S1 base per phase is the original formula.
Okay, sir.
As we have a flexibility to say V base line to line equals to √3 into V base per phase in the transmission lines and star connections,
Okay,
you are
sir.
modifying this formula into line to line base voltage square by S base 3 phase.
Okay, sir.
Understanding? But this is a basic formula. You use this formula only always. Nothing will go wrong.
Okay, sir. Okay, sir. Sir, if
Okay.
I have to calculate Z2 base per phase, what the
Then
ratings I
again
can
you take
add?
V1 base per phase by S1 base per phase.
Okay, sir.
Sir, V2 base per phase by S2 base per phase. What is the
Sir,
V2
there
base
it
per
connect-
phase? V2 base per phase.
sir,
Secondary connection.
There it's the star, no, sir.
Star. Then it will come 4n by √3.
Sir, finally, should it satisfy the condition that Z1 equal to K square into Z2? That equation there, no, sir.
That condition may come, may not come. Because
Not
how you are
compulsory.
considering that K, that's the issue.
Okay,
Is it
sir.
the phase transformation ratio or line to line transformation ratio? If it's a phase transformation ratio, you may get.
Okay, sir.
What is the phase transformation ratio here? 400 by √3 by 11,000.
Yes, sir.
400 by √3 secondary. Primary 11,000.
Okay, sir.
That's the K. So Z02 equals to K square into Z01. You do that. You get the effective impedance referred to secondary side. That's the phase winding impedance.
Okay, sir.
Okay?
Okay, sir. Thank you, sir.
Shiva. J Shiva.
Hello, sir.
Tell me, Shiva.
Sir, at 92 Fs.
What is that?
92 Fs.
92. Okay.
Sir, here you said that the secondary of the first transformer voltage should matches with the primary of the second transformer. Can you explain it again, sir?
Can you please repeat again?
No, sir, the secondary voltage of the first transformer winding should match with the voltage of the
Yeah.
primary.
See, actually for proper connection or proper synchronization, listen to me.
Yes, sir.
This winding voltage I decided as 132 kV.
Okay, sir.
Are you looking at this winding?
Yes, sir. Yes, sir.
Okay. After deciding that this winding voltage is 132, your line will operate at 130 kV.
Yes, sir.
So obviously, whatever the transformer winding you connect at other end of line,
Okay, sir.
whatever the transformer winding you connect at other end of line, that winding voltage rating should be close to 130 kV. Then only it's a proper connection.
Okay, sir.
Getting me?
Yes, yes, sir.
So
And
that's why I selected this value 130 kV.
Okay, sir. So this condition should be applied for all the apparatus in
All,
house
yes.
voltage.
Wherever you are connecting, that voltage rating should match. If you are connecting two apparatus together,
Yes, sir. Their voltage rating should be.
voltage rating should be matched, right? That's one of the conditions for synchronization.
Okay, sir. And then in 115, sir, 115.
115. Okay.
Sir, can you explain the fault level is equal to infinity?
Simple, no? You take fault at this bus, fault at the fourth node. Fault means you take a short circuit here.
Yes, sir.
Then this voltage experiencing zero impedance.
Okay, sir.
Voltage by zero, how much?
Yeah, yes, yes.
Infinite.
Yes.
Okay.
Okay, so that's it.
Yeah.
Thank you.
Okay. Shrujana.
Good evening, sir.
Good evening.
Sir, in last problem, that three transformers are connected using single transformer.
Yeah. Tell me, what's the doubt you have in that?
Sir, can you explain that how you took 0.2 in star and delta? I didn't understood, sir.
See, actually, each transformer effective impedance is 0.2 per unit. Huh?
Yes, sir.
Okay. So these are 3 windings. 3 windings on primary, 3 windings on secondary.
Yes, sir.
See, that 0.2 per unit, either you have to take onto secondary side or you have to take onto the primary side.
Okay, sir.
Let us take on secondary side.
Mm.
So this reactance 0.2, this reactance 0.2, this reactance 0.2. These 3 reactances will be 0.
Okay, sir.
It will act as ideal winding. Then those 0.2 per unit reactances, I have drawn something like this.
Okay, sir.
So what is the per phase impedance here? 0.2 per unit only, right?
Yes, sir.
Rather than taking those 0.2 per unit impedance on the star side, you can keep them on the delta side also.
Okay, sir.
That's your wish, right?
So we
Any
can
side
take
you
either on star or delta.
any
Okay.
side you can take. 0.2 per unit on delta side also you can take.
Okay, sir.
But generally, if you are doing per phase analysis, if there is any delta, that you have to convert into star, right?
Yes, sir.
If you convert that into star, it will be remain same as 0.2.
Yes, sir.
Star side I have shown 0, delta side I have shown 0.2. If you convert this delta connected 0.2 to star, you get 0.2 only.
Yes, sir.
Understood, Surjana?
Thank you, sir. Yes, sir.
Any doubt
Yes,
here?
sir.
Any doubt?
No, sir. No, sir.
Okay, okay. Nagatej. Naga Nitej.
గుడ్ ఈవినింగ్ సార్.
Good evening.
సార్ నాకు ఎక్కడ డౌట్ ఉందండి సార్, అడ్వాంటేజెస్ లో డౌట్ ఉంది సార్.
Okay.
సార్ ఇప్పుడు నార్మల్ గా ఇంపిడెన్స్ ని కంపేర్ చేసేటప్పుడు పర్ యూనిట్ లో తీసుకొని కంపేర్ చేసాం కదా సార్.
ఎస్ ఎస్
సార్ ఫస్ట్ దానికేమో సపరేట్ గా బేసిస్ వాల్యూ తోటి డివైడ్ చేసి చేసాం సార్. సెకండ్ దానికి అంటే ఫోర్త్ దానికి
Nitej, if both generators are connected together existing in the same system,
yes sir,
then you should choose a common base for the comparison.
Okay sir.
But if these 2 generators are operating separately,
yes sir,
you have to take base values as their own ratings.
Okay. Generally అలానే చేయాలి సార్ ఇప్పుడు.
Yes. If it's a connected system, you have to go with a common base.
Okay sir.
But if it's not a connected system, you should choose their ratings as base values to decide which reactance is more.
Okay sir.
Okay.
Thank you sir.
Okay. Anil Kumar.
Sir,
Anil Kumar.
good evening, sir.
Good evening,
sir.
Anil Kumar.
Sir, 88F.
Tell me.
Sir, can you explain this, sir, how Z01 equal to 0.02 plus J? Sir, per unit impedance of a transformer, sir.
Yeah.
How will be same, sir, refer to primary?
No, actually in the problem, he said simply per unit impedance of transformer. 0.02 plus 0.07 J. It's simply transformer impedance per unit.
Okay, sir.
Means this is nothing but effective impedance of transformer, either referred to primary side or referred to secondary side.
Oh, sir.
So we can write this ZT either as Z01 per unit, or you can write the same thing as Z02 per unit also.
Okay, sir.
Okay?
Okay, sir. Sir, and I have another doubt, sir. In a symmetrical component, for an unbalanced system, we cannot drive, sir. It is difficult to drive.
Difficult to?
Drive, sir. Solve, sir. Difficult to solve.
We will discuss that in tomorrow class. Once you just listen to the next lecture.
Okay, sir. Okay.
You will get some clarity.
Okay, sir. Okay, sir. Thank you, sir.
After that, still if you have doubt, you can ask me tomorrow. Better.
Okay, sir. Okay.
Okay.
Thank you, sir.
Iyappan, yes.
Sir, in the transformer per unit impedance calculation circuit, sir.
Okay.
The per unit transformer impedance calculation, either primary or secondary, which rating best use, right, sir? Primary or secondary side?
That's your wish. Both, anything will give same number.
Anything will same. Okay, sir. Understood.
Okay, anything. Any side you take. Old, but if you are sticking on to primary, old and new bases, you should take on primary side only.
Okay, sir. Okay.
If you are sticking on secondary, you should take old and new base on the secondary side.
Same side.
Same side you should do calculation.
Either side, no problem, sir.
No problem, no problem.
Sir, okay, sir. Okay, understood.
Okay, yeah.
Okay.
Mridul Sharma.
Hello.
Mridul, tell me, Mridul.
Hello, good evening, sir.
Good evening.
Sir, my question is regarding this only, the page that has been open right now. Could you please turn on to the next page where you have found the phase impedance of transformer referred to the primary? Yeah, sir, okay. I'm having problem in this section only. Rest I understood. I'm not able to understand this Z01 per unit into Z1 base. Why we did that, sir?
Which side you want to find impedance in ohms?
Yes.
Which side you want to find the?
It's referred to the primary, sir.
Primary. So you have to multiply per unit impedance with primary base only, right?
We have to multiply the
per unit impedance with the primary base.
Yes.
That's it.
Okay, the Z1 base per phase that we have calculated is for the primary phase. Yeah.
Primary.
And this Z01 per unit, it will be same for both sides. Yes.
Both sides.
So if we are going to calculate it for secondary, we can do the same thing by calculating the per phase for the secondary side. Yeah. Yes. And then we can simply multiply it and we'll be able to get the phase impedance of the transformer referred. Yeah. Okay, sir. Thanks a lot, sir. Thanks a lot. Okay. Have a good night, sir.
Yeah.
Bye.
Good night. Shamala.
Good evening, sir.
Good evening, Shamala. Tell me.
Sir, you said like Z01 K square equal to Z02. Where K we have to take phase transformation ratio.
Phase transformation ratio. Yes, correct.
Sir, how we know like we have to take phase transformation ratio or line transformation?
What impedances you are comparing?
Sir?
What impedances you are comparing? You said Z02 equals to K square into Z01, right?
Yes.
What is it? Z02 and Z01?
Phase impedance.
That's it.
Okay. Like if we have the delta star connection, so then
there is no meaning for line.
Yeah, I got.
There is no meaning for Z02 line to line, Z01 line to line.
Yes, sir. So in that case, K we had to take phase transformation ratio.
Yes.
Okay. Thank you.
Okay. Tulsi.
Hello, sir.
Tell me, Tulsi.
Sir, 87F, sir.
Okay.
సార్ ఇప్పుడు మనము ఎప్పుడు వైండింగ్ అది నాకు అర్థం కావడం లేదు సార్.
ఏదమ్మా?
ఇప్పుడు వైండింగ్ ని ఎప్పుడు కన్సిడర్ చేయాలి, లైన్ ఎప్పుడు కన్సిడర్ చేయాలి సార్ కన్వర్షన్స్ లో?
ఇప్పుడు ఇక్కడ ట్రాన్స్ఫార్మర్ ఇంపెడెన్స్ క్యాలిక్యులేట్ చేయమని అడిగితే వైండింగ్ చూడండి.
ఓకే సార్.
ట్రాన్స్ఫార్మర్ అడగకుండా జస్ట్ మీకు ఒక సింగిల్ లైన్ డయాగ్రామ్ లో ఇచ్చినప్పుడు మీరు వైండింగ్ గురించి పట్టించుకోవద్దు అసలు.
ఓకే. ఇప్పుడు ఇక్కడ మనకి ట్రాన్స్ఫార్మర్ ఒకటే ఉంది కాబట్టి
ట్రాన్స్ఫార్మర్ కి అడిగారు కదా ఇక్కడ ఈ ప్రాబ్లం లో.
ఎస్ సార్.
ఓకే.
ఓకే, థ్యాంక్ యూ సార్. నెక్స్ట్ 92F సార్. సార్ ఇక్కడ ఫోర్త్ పాయింట్ ఇంకోసారి ఎక్స్ప్లెయిన్ చేస్తారు.
ఓకే. సో దిస్ ఈస్ వన్ సింగిల్ లైన్ డయాగ్రామ్. I have given already. These are rated voltages. 11 kV by 130 kV, 130 kV by 6.6 kV. These are rated voltages.
Okay, sir.
At present, operating voltage at bus 1 is 10 kV. Operating voltage at bus 4 is 10 kV, 7 kV.
Okay.
The question is, which bus voltage is more? Is it bus 1 or bus 4? Okay. But that comparison I can't make directly because of these transformers existence.
Okay, sir.
Direct గా మనం ఈ 10 kV ని 7 kV ని కంపేర్ చేయకూడదు. ఎందుకంటే ట్రాన్స్ఫార్మర్స్ ఉన్నాయి కాబట్టి. ఒకవేళ ట్రాన్స్ఫార్మర్స్ కనుక లేకపోతే మధ్యలో మనం సింపుల్ గా అబ్సల్యూట్ వాల్యూ కంపేర్ చేసి ఏ వోల్టేజ్ ఎక్కువ ఉందో చెప్తాం.
ఓకే.
సో ఇప్పుడు ఏం చేయాలి? ఈ కంపారిజన్ చేయాలంటే పర్ యూనిట్ లో తీసుకోవాలి. పర్ యూనిట్ లో తీసుకోవాలంటే ఈ బస్ 1 దగ్గర ఒక బేస్ వోల్టేజ్ అనుకోండి. ఆ బేస్ వోల్టేజ్ ట్రాన్స్ఫార్మ్ చేస్తూ బస్ 4 దగ్గర బేస్ వోల్టేజ్ ఎంత అవుతుందో క్యాలిక్యులేట్ చేయండి.
ఓకే సార్.
అప్పుడు బస్ 1 వోల్టేజ్ పర్ యూనిట్ కనుక్కోండి, బస్ 4 వోల్టేజ్ పర్ యూనిట్ కనుక్కోండి.
ఓకే.
అప్పుడు కంపేర్ చేయాలి రెండు.
ఓకే.
That's why I assumed that base voltage at this location is 11 kV.
11 kV.
Transform to the line side, 130 kV it came.
Okay.
Transform to the load side, it came 6.7 kV.
Okay.
Then V1 per unit, operating voltage 10, base voltage 11, 10 by 11 is the operating voltage at bus 1. Bus 4 voltage operating 7 by 6.7.
7.
That is coming more definitely.
Okay.
Actually, this comparison between bus voltages will be more needed, particularly if you want to know direction of reactive power flow in the system.
What, sir?
Reactive power flow.
Okay, sir.
Generally, reactive power will flow from higher voltage magnitude bus to lower voltage magnitude bus.
Okay.
But just by looking at this bus voltage is 10 kV, 7 kV, I can't say from which bus to which bus reactive power is flowing.
Yes, sir.
But by converting these things into per unit power, I confirmed that V4 is more compared to V1.
Okay.
So I can say reactive power may flow from bus 4 to bus 1.
To bus 1. I got it.
For those things, these per unit quantities are more needed.
Okay.
Okay. If you don't have transformer, per unit absolute will be same. No change at all. If you have transformers in the system, there comes the significance of the per unit quantities.
Okay.
Okay. Yeah.
That అప్పుడు చెప్తున్నారు కానీ సార్ బేస్ వాల్యూ రేటింగ్స్ ని మనం బేస్ వాల్యూస్ గా కన్సిడర్ చేయకూడదు. ఆ పాయింట్ ఇంకోసారి చెప్పగలరు?
రేటింగ్స్ ని బేస్ వాల్యూగా కన్సిడర్ చేయకూడదా?
అంటే ఫస్ట్ లో ఒక డౌట్ అడిగినప్పుడు చెప్పారు సార్.
యువర్ విష్ ఇట్ ఈస్ యాక్చువల్లీ what are the base values I have to select? Either you can select ratings as a base value or any other numbers you can select as base values.
Okay, sir.
Okay.
Okay.
Elaborate your doubt.
ఇప్పుడు ఫస్ట్ లో నేను చెప్పారు అని చెప్పి ఒక అమ్మాయి డౌట్ అడిగింది సార్. బేస్ రేటింగ్స్ ని బేస్ వాల్యూస్ గా కన్సిడర్ చేయకూడదు, కానీ మనం రేటింగ్స్ ని కన్సిడర్ చేస్తున్నాము అని అడిగింది సార్.
Actually what she said is sir, earlier you said that ratings need not to be base values.
Yes sir.
But you have chosen ratings itself as base values. That's the question.
Yes sir.
See the statement, ratings need not to be the base values. Is it the meaning to say ratings will not become base values?
No sir, ratings can become base values.
Ratings can become. That's what I clarified. Ratings can be taken as base values or cannot be taken as base values. That's our wish, as well as according to the problem statement they have given.
Okay sir, I got it.
Okay.
Yes sir. Sir, in 4F sir.
Today's class or yesterday's class?
Today's class only sir.
Today I can't open that slide.
Okay.
You tell me.
The decoupled equations, coupled, I didn't get that sir. Coupled equations.
Actually, if it's a three-phase balanced system, you can do the phase A analysis separate.
Yes. Yes sir.
Phase B analysis separate, phase C analysis separate.
Yes sir.
But if it's an unbalanced system, you have to do three-phase analysis.
Means I didn't. We can consider the phase and do solve the equation.
Neutral voltages may not be zero.
Yes sir.
In the balanced system, neutral voltages are zero. That's why we are applying KVL for phase A separate, phase B separate, phase C separate.
Yes sir.
But in the unbalanced system, neutral voltages may not be zero. We don't know where we have zero potential.
Yes sir.
At that time, you have to apply KVL between phase A and phase B, phase B and phase C, phase C and phase A.
Okay sir.
So 3 KVL equations, but these 3 equations I can't solve independently. I should solve 3 equations at a time.
Okay.
These are coupled.
Okay, I got it.
Okay.
Sir, another doubt sir. Z02 is equals to K square into Z01. That point.
Yeah.
Per unit, I didn't get that point sir.
Per unit.
Per unit transformation ratio, we are considering it now, sir.
Okay.
My doubt is, if we take the K value is equals to 1, then V1 is equals to V2 can also.
Per unit.
Yes, E point is.
Per unit, V1 per unit equals to V2 per unit, right?
సరే మనం నిన్న ప్రాబ్లమ్ సాల్వ్ చేసేటప్పుడు V1 ఓకే పర్ యూనిట్ కాదు సార్ అది ఓకే సార్
ఓకే
ఓకే థ్యాంక్ యూ
సార్ భరత్ Bharat, tell me.
I don't have any doubts in this topic, sir, but I have one query that a Telegram group is formed for us, for our batch, sir. So some of us are not a part of it. So if you could...
you put a request to me, to my number.
To your number, sir?
Number 96184-61918.
Okay. Thank you, sir.
Mohammed Mubin.
Yes, sir.
Tell me.
Sir, yesterday we have a problem solved on. The question is like a 3-phase synchronous generator rated for 22 kV 100 MVA.
Okay. What's the doubt you have in that?
Sir, in that you have given homework to find real and reactive parts. Old base voltage, old base power is given. New base voltage, new base power is also given.
Okay.
And in between a sentence given like excess of generator equal to 1 per unit, it gives real power of 0.6 per unit at 0.8 pf lag.
Okay.
With 20 kV terminal voltage.
Okay.
In that I have solved for reactance of generator and terminal voltage per unit values, but reactive power per unit values, how to find?
We have solved that problem, I think, in the class itself.
So please tell once again.
Yeah. This problem only, right? This one only, right?
3-phase.
We have solved it. It is the second one I have taken PG per unit.
Yeah, this one only, sir.
You want to copy?
No copy, sir. Please, first one understood. Second one, how we took, sir?
Very simple. I am asking one question to you. How to calculate real power per unit?
Per real power by S base.
That's it. I have written that statement here.
Okay.
What is real power actual? Volt per unit value into S base volt.
How that, sir?
Okay. What is PG? Real power. How to calculate real power from per unit value given?
Per unit into base only. But that's how about old, sir? Why we are taking old? We are to follow.
Because absolute value will be remain same, right?
Okay. Absolute value will remain. Okay. Yes, sir.
Absolute value, whether you calculate from old base values or new base values, it will be same.
Yes, got it. Sir, next page, sir, please forward.
Yeah.
The Q also the same or okay, we have
directly calculate from PG per unit new here. QG, I didn't consider the old value. Already power factor I know remains same.
Yeah, I know. If we are not having power factor, we can go by that method. Else this, yeah.
Yes.
Okay. Got it, sir.
Okay.
Sir, one more, sir. Can I ask? Sir, I want to brief. I mean, important points. I have noted some points. Please correct it if they are wrong. Sir, if you're converting delta to star or star to delta, the actual value will change, but the per unit value remains same. Sir?
If it's a 3-phase.
If it's a 3-phase, yes. And in transformer, Z01 per unit equal to Z02 per unit equal to Z1 per unit plus Z2 per unit.
But Z1 per unit on primary base, Z2 per unit on secondary base.
Okay, that I'm not written. Okay, sir.
Z01 per unit on primary base. Z02 per unit on secondary base.
Yeah, okay. Thank you, sir. Okay, done, sir. Thank you.
Yeah. Now, Mubin.
Hello, sir.
Sai Charan, tell me.
Sir, in page number 92, sir.
Okay.
Sir, here up to we arrive to a transformer winding. Up to that what voltage is there? We should consider that voltage only without without considering the line voltage drop, no, sir?
See, these are ratings, right? Charan.
Yes, sir.
These are ratings, right?
Yes, sir. Transformer ratings.
Then you don't need to bother about voltage drop.
Okay, sir.
If you are thinking about operating voltage and all, you have to think about voltage drops.
Sir, here you wrote 130 kV, sir, here in prime.
I have written those what we call rating. Rating as 130 kV. I have given.
No, sir. I'm just asking, sir. You wrote here 130 kV, no, sir. Can you please 93, yes, sir, 93.
93. Okay. What you have here down?
Here 132 kV is up to the primary winding of second transformer, no, sir.
What is it? What is that 130 kV you are talking?
Base value.
Base. Okay, good. Base value up to primary 130 kV.
So with respect to this base value, can we confirm that this 130 kV is a operating voltage at the primary?
No. 130 kV is a rated voltage of the winding.
Sir, I got confusion here only, sir. Is that
listen.
With respect to...
Can I say rated voltages and base voltages are equal?
No, sir.
Need not to be.
No, sir. No, need not to be. Yes, sir.
Need not to be. Then what is the rated voltage of this winding?
Sir, rated 130 kV, sir.
130. What is the base voltage at this winding location?
Okay, sir. 132 kV.
Need not to be equal, I said.
Yes, sir. So if we won't arrive to a transformer winding, we should consider that voltage only up to the transformer winding, and after arriving that, we should take that transformation
ratio to find out base on the other side.
Okay, sir. Okay. Thank you, sir.
Yeah.
Okay, sir.
Fine. Muralidhar.
Sir, I not understand 2 point. Synchronous machine with rotor rotating at a synchronous speed for infinite bus. And
you tell me what is the frequency of the infinite bus?
Yes, sir.
What's the frequency of infinite bus?
Maybe 50 hertz.
Constant?
Yes, constant.
Who will decide frequency?
Oh, not understand.
Who will decide frequency of operation generally? Formula for frequency?
What?
Formula for frequency? Pm by 120?
Yes, sir.
Number of poles into speed by 120. Listening to me?
Sir, not understand. Please repeat.
Frequency equals to Pm by 120.
Yes, sir.
P will be number of poles.
Yes.
N will be speed. Number of poles will be constant always.
Yes.
For a given machine.
Yes.
Then if frequency is constant, speed must be constant, right?
Yes.
Means it's a synchronous machine with the constant frequency, means it is rotating at synchronous speed always.
Hello, sir.
It is rotating at synchronous speed always.
Hello? Yes, sir.
Yeah. I think you didn't get me.
Hello? Yes, sir.
1 minute, please. Is there any problem with mic? Yeah, you see this. Frequency F equals to 120, Pm by 120. Are you listening to me, Diksha? Diksha, are you listening to me?
Sir, now Listen.
Okay, frequency equals to Pm by 120. Please kindly respond. Please kindly respond, Diksha. Are you listening to me, Diksha?
Yes, sir. Yes, sir.
Frequency equals to Pm by 120.
Yes, sir.
Number of poles will be constant always.
Yes.
Then if frequency is constant, then obviously speed will be constant, right?
Yes.
Speed will be constant. Following?
Yes, sir. Okay, sir.
See, speed is constant in the sense, listen to me.
Yes, sir.
Irrespective of any disturbance you create, it will rotate at a constant speed.
Okay, sir.
Then can I say it is having infinite inertia? Infinite inertia. Yes or no? Yeah. Anybody? Please raise your hands if anybody is listening to me. Frequency is constant. I will say speed is constant irrespective of the disturbances. Can I feel that rotating body is having infinite inertia or infinite weight? Infinite weight. For example, you see Earth. It may do one rotation in one day. For example, if you kick Earth with a great force, will it reduce its speed of rotation? Will it increase its speed of rotation? What is the inertia of Earth? Infinite. But still it is rotating, right?
Yes, sir. Understood, sir.
That is a type of machine we are imagining here. Okay?
Sir, I have also problem in isolation transformation. In isolation transformer, we take the transformer ratio K equals to 1. The transformer ratio and the K notation is same or not? K value is also 1.0 plus J 0.0.
K value. What is that K value? 1.0 plus J 0.0.
K notation.
What K notation? Can you tell me? What is that K notation?
It is used in the symmetrical component.
That is different. This K is different.
Okay.
Electrical components K is different. This K is different. Notations these are.
Sir, I have also regarding the not regarding the topic. Delta winding is a closed winding or open winding, because the
Closed.
delta winding reconnection is possible. We converted into star.
Delta winding is a closed winding. That's it.
Okay.
Converting into star, you are asking me, delta to star.
Then open winding.
Say, Diksha,
Yes.
physically are you reconnecting delta to star or on the paper?
Paper, on paper.
On the paper means it will be a closed winding physically, right?
Okay, sir.
Understanding?
Yes, sir.
Yeah. Physically delta you reconnect into star. It will be star only. It won't be delta further.
Okay, sir.
Okay?
Yes.
Yeah. Any other doubt you have, Diksha?
No, sir. Thank you, sir.
Yeah, fine.
Sir.
Mohammed.
Sir, I have a doubt in transformer, sir. Sir, we have primary side V1 base, secondary side V2 base, and the transformer ratio is V1 and V2. I mean V2 by V1.
V2 by V1 equals to V2 base by V1 base.
Yes, sir, that is clear. But if we have three-phase transformer, then we take
phase voltages, winding voltage, winding.
Yes, sir, winding voltages. If it is a delta star delta, we should go for phase voltages only, then we go for base, right, sir? Sir, but in the question we have solved, it is getting for line values also. Is it applicable for all or only this case, sir?
For all it will be applicable.
We have taken line, sir. I'm asking about.
Irrespective of your transformer connection, if you know primary line to line base.
Yes, sir.
secondary line to line base. See that ratio V2 base line to line by V1 base line to line equals to V2 line to line by V1 line to line.
Okay.
V2 base per
Irrespective of
phase
the
by
winding.
V1 base per phase equals to V2 per phase by V1 per phase.
Okay, got it. Thank you, sir.
Hello, sir.
Who is this?
Sir,
Charan, tell me.
Sir, do you have Telegram on this number, sir?
Yeah, I have.
Sir, it is not coming while I'm searching, sir.
You put in WhatsApp else.
Okay, sir.
Or you put a text message. Anything.
Okay, sir.
Ganesh. Sorry, I am really sorry. Is Ganeshwari, if I'm not wrong. Kakarapalli Ganeshwari. Any doubt you have?
Yes, sir.
Do you have any doubt?
Yes, sir. Please explain that delta connection 0.2 0.2. That
Yesterday
question.
we have done. Have you followed yesterday class?
Yes, sir, but I didn't get that, sir.
Delta to star conversion, you don't get any change in the per unit number.
Yes, sir. Okay, sir. But if you okay, sir. Per unit for delta to star. Nothing, sir.
Actually, Ganeshwari,
yes,
if you are converting delta to star absolute values,
okay, sir.
Absolute value will become by 3.
By 3, sir. Yes, sir.
Okay. In the similar way, after converting delta to star, base impedance also becomes by 3.
Yes, sir.
So absolute value by base value is a per unit number, right?
Yes, sir.
Absolute value became by 3. Base impedance also became by 3.
Yes, sir.
By 3 by 3 cancelled out.
Per unit same. Okay, sir. Okay, sir.
How in the sense, just you go through the previous lecture ones.
Okay, sir.
Okay.
Thank you, sir. That's it, sir.
Okay. So anybody have a doubt? You can raise your hands. Anybody having a doubt? Please kindly raise your hands. Akash.
Sir, good evening, sir.
Good evening, Akash. Tell me.
Sir, my doubt is there any drawback of using per unit system? We are using it for solving. Is there any problem? Drawback like approximating the problem?
Actually, I don't say it's a drawback. I will say it's one of the assumption actually.
Okay.
If it's a delta star transformer or star delta transformer, if there will be a phase shift of 30 degree or minus 30 degree, 210 degree, 150 degree.
There will be phase shift of 150.
Definitely, there is a phase shift in delta star and star delta transformers, right?
Yes, sir.
That phase shift I can't consider if you are doing calculations in the per unit level.
Okay.
Okay.
Thank you, sir. Yes.
That's not disadvantage actually. That is one of the assumption we feel. Otherwise, we don't find any disadvantage of using per unit.
And sir, in the single line diagram, we are approximating everything, all in a single line. By removing the mutual, there will be no
mutual. We are removing by a proper transformation, not just like that.
Everything will be balanced.
Yeah, everything will be obviously numerically balanced.
Okay.
Right. After that, if you convert that per unit numbers back into absolute, you should get absolute values exactly.
Okay.
Okay.
Okay, sir. Thank you.
Okay. Ajay.
Good evening, sir.
Good evening, Ajay. Tell me.
సార్ మీరు చెప్పింది కదా సార్, అంటే లైన్ స్టార్ టు డెల్టా కన్వర్ట్ చేసినాక మనం మామూలుగా అంటే స్టార్ డెల్టా ఉన్నప్పుడు లైన్ వోల్టేజ్ ని బై √3 అని తీసుకుంటాం కదా సార్, బోత్ సైడ్ ప్రైమరీ సైడ్ సెకండ్ సైడ్. అది అంటే మనం జనరల్ అంటే ఎవ్రీ టైం యూజ్ చేస్తాం సార్ అట్లా ఏ ప్రాబ్లం చేసినప్పుడు?
చూడండి ఒకసారి. The transformer tank.
Yes, sir.
You don't know what type of windings you have inside.
Yes, sir.
It's not visible to me, and nameplate is also not visible.
Yes, sir.
But I know primary voltage rating is 765 kV. Secondary winding rating is 400 kV.
Okay, sir.
What is 765 kV? Line to line voltage rating of the primary.
Yes, sir.
What is that 400 kV? Line to line voltage rating of the secondary.
Secondary size.
Okay. Now, what is this terminal voltage? Primary terminal voltage is how much? Terminal means terminal to ground, right?
Yes, sir.
How much? 765 kV by √3.
Yes, sir.
What is this terminal voltage?
400 kV by √3.
That's it. Now, what's your doubt?
అంటే ఓకే సార్, అర్థమైంది సార్. అంటే కొంచెం డౌట్ ఉంది సార్.
ఓకే
ఓకే సార్.
ఏదంటే ఒక సింపుల్ ఇలా అనుకోండి, డెల్టాని స్టార్ లో కన్వర్ట్ చేస్తాం అనుకోండి.
ఓకే సార్.
ఓకే
ఓకే సార్.
ఫైన్. ఎనీ అదర్ డౌట్ యూ హావ్?
ఓకే సార్. అంటే సార్ ఇది ట్రాన్స్మిషన్ కూడా సేమ్ ఉంటది, డిస్ట్రిబ్యూషన్ కూడా సేమ్ ఉంటది సార్ ఇది?
ఎనీవేర్ ఎక్కడైనా ఎనీ సిస్టమ్ ఇఫ్ యూ హ్యావ్ 3 terminals. Okay, 3 terminals, you know line to line voltage.
Yes, sir.
Then terminal voltage means terminal to ground voltage. Terminal to ground will be that voltage by √3, line to line voltage by √3.
Okay, sir.
Okay.
Okay, sir. Okay. Thank you so much.
Yeah. Sridevi. Sridevi.
Sir, good evening, sir.
Good evening. Tell me, Sridevi.
Sir, yesterday you have given a homework to calculate the generator impedance magnitude in per unit form and also apparent power in per unit form.
Okay.
Sir, I have calculated the generated impedance in per unit, but I could not calculate the apparent power in per unit form. Could you please help me, sir?
Do you know real power in per unit?
Yes, sir.
Reactive power in per unit?
Yes, sir. I have
Complex power?
The square root of this real
square plus
and
square. That is
yes.
apparent, right?
Yes, yes. And that means apparent power actual by S base.
S base, yes, correct.
S base is already taken as 100 MVA. Sir, what will be the answer to this, sir?
Can you please tell me what's the P per unit and Q per unit? I think 0.3. P per unit is 0.3 new. 0.3 only, I think.
And Q per unit?
0.3 into 0.6 by 0.8. Is it 0.8 lagging power factor?
0.9, sir.
Okay. Then what is that number? .333. Apparent power 0.333.
Okay, sir.
Get him?
Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Okay. Vedagopal Reddy.
Yes, sir. Good evening, sir. Sir, after break, I have some confusion in Z Thevenin. Sir.
Tell me, get Thevenin. What's the doubt you have?
Z Thevenin, how you are taking, have confusion, sir.
Confusion you have there?
After, sir, after circuit, after impedance circuit, you calculate Z Thevenin, sir.
Yeah.
I have confusion how you are calculating Z Thevenin.
Yes, you might have studied in network analysis.
Yes.
Yeah.
Sir.
You have studied this in network analysis, right?
Yes, sir.
Yeah.
I have studied.
Network simplification.
Yeah, yes, sir. But you mentioned in question node 1, node 2, something like that. That means how we are getting, sir, how we are simplifying it is.
No, see, actually, with respect to node 1, you have to find, right?
Yes, sir.
And if you see on the left side, you have only one impedance in a closed way.
Yes, sir.
That is J0.9917.
Yes, sir.
On the right side, I have 3 impedances, but it is closed.
Yes, sir.
So the overall impedance is J0.4755.
Okay, sir.
Parallel combination of these two impedances is nothing but Z Thevenin.
Yes, sir. Both are in parallel.
Parallel, right?
Yes, sir. Yes. Okay, sir.
Okay.
Thank you. Okay,
Yeah.
sir. Thank you.
Yogashri.
Sir.
Tell me.
సార్ స్టార్ లో కనెక్ట్ చేసినప్పుడు డెల్టా అంటే డెల్టా కనెక్ట్ చేసినప్పుడు షార్ట్ చేస్తాం కదా సార్ సార్
Tell me again.
మనం స్టార్ కి షార్ట్ చేయము డెల్టా కి షార్ట్ చేస్తాం కదా సార్ అప్పుడు తేడా చూపిస్తుంది కదా సార్ అప్పుడు సేమ్ ఎట్లా తీసుకుంటాం వోల్టేజ్ అంటే వోల్టేజ్ డెల్టా కనెక్ట్ చేసినప్పుడు ఆర్ డాష్ కానీ వై డాష్ బి డాష్ మొత్తం షార్ట్ చేస్తాం కదా సార్ అంటే ఒకదానికి ఒకటి టచ్ అవుతుంది కదా సార్ మొత్తం
But you have that positive negative terminals, right?
ఎస్ కనెక్షన్స్ ఇచ్చినప్పుడు షార్ట్ చేస్తాం కదా సార్ డెల్టాలో
Okay, if you feel it's a short, you find out what is that loop voltage.
అంటే మీరు వోల్టేజ్ చేసినప్పుడు v/√3 అని చెప్పారు కదా సార్ దీనికి దానికి కొంచెం తేడా ఉంటుంది కదా సార్ అంటే డెల్టాలో కనెక్ట్ చేసినప్పుడు స్టార్ లో కనెక్ట్ చేసినప్పుడు అట్లా ఎలా ఏముంటుంది అని అడుగుతుంది
ఏ పేజ్ లో డౌట్ ఉందమ్మా మీకు
ఇదే పేజ్ లో మీరు ఇప్పుడు చెప్పారు కదా సార్ వోల్టేజ్ v/√3 తీసుకుంటాము
యాంగిల్స్
డెల్టా
ఉంటాయి కదా యాంగిల్స్ చూపించలేదు ఇక్కడ యాంగిల్ 0 డిగ్రీ -120 డిగ్రీ +120 డిగ్రీ యాంగిల్స్ ఉంటాయి కదా
ఓకే సార్
ఓకేనా
అంటే డెల్టా అయితే మనము కనెక్షన్స్ ఇచ్చినప్పుడు షార్ట్ చేస్తాం కదా సార్ అట్లాగా తేడా ఉంటుంది
ఇక్కడ చూడొచ్చు plus minus 400 kV at an angle 0 degree. Okay na?
Okay.
Plus minus 400 kV at an angle -120. Plus minus 400 kV at an angle +120. Okay na?
Okay.
What is the loop voltage? KVL apply cheyandi loop ki. KVL.
Oh. 400 at angle 0.
ఎంత వస్తుంది KVL అప్లై చేస్తే?
Sir, wait, sir.
జీరో కదమ్మా యోగేశ్వరి.
Sir,
Sum of the 3 voltages, that's a KVL, right?
400 at angle 0 ఉంటుంది.
0. You will get answer 0. Okay.
Okay, sir. Okay, sir.
What is the problem of short circuit?
నా డౌట్ వచ్చేసి ఏంటంటే సార్, ఇప్పుడు స్టార్ లో కనెక్ట్ చేసినప్పుడు డెల్టాలో కనెక్ట్ చేసినప్పుడు తేడా ఉంటుంది కదా సార్ అని అడుగుతున్నాను సార్.
Definitely have a difference.
అప్పుడు వోల్టేజ్ V/√3 అని తీసుకుంటున్నాం కదా సార్.
Terminal to ground. Not terminal to terminal. Terminal to ground, right?
Okay, sir. Okay, terminal to terminal అయితే direct voltage.
Obviously, it is line to line voltage.
Okay.
Okay.
Okay, sir.
Any other doubt you have, Yogeshri?
No, sir.
Okay. Anil, Kalepo Anil. Tell me, Anil. Anil, do you have any doubt, Anil?
Yes, sir. Are you able to hear me, sir?
Tell me.
Sir, in this, if you can apply KVL, at the time of the transformers, we learn, sir. ఇక్కడ polarity, depending upon polarity, ఇక్కడ చూడండి సార్, మైనస్ కనెక్ట్ అయ్యింది కాబట్టి ఇక్కడ మనకి వోల్టేజ్ రైజ్ అవుతుంది.
Sorry.
That is only my
doubt. It's a mistake of me. Okay, I'm really sorry.
That is only the doubts. Okay, sir. Thank you, sir.
So, any other doubts you have? Please raise your hands. Else we can leave. We can close the session. Naveen.
Sir, you didn't uploaded the last class notes, sir.
Ask me in Telegram.
Okay, sir. Okay, sir. In that group there, no, sir. Power systems.
You just put me in Telegram.
Okay, sir. Okay, sir. Thank you, sir.
So, any other doubts? So, can I close the meeting? Yeah, if you have any doubt, you can contact my number also, mobile number. 9618461918. So I think I can leave. Can I leave?
Yes, sir.
Yeah, thank you.